Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And good morning, everyone. Welcome to the second day of iNUSTEC2021. I hope you had a very good rest yesterday. So this morning, we will continue the conference with two keynotes. So the first keynote, keynote number 5, will be delivered by Professor Dr. Lee Do-jung from Ulsan National Institute of Science and Technology, South Korea. The title of his presentation is Nuclear Core Analysis and Methodology Development. And we will proceed with the next keynote entitled Nuclear Engineering, First Overseas HPR 1000 Project, which will be delivered by Mr. Ding Jian from CNNC, China Zongyuan Engineering Corporation, China. Okay, so the first, these two keynotes will be chaired by Dr. Nur Shazwani binti Muhammad Ali from UTM. So without further ado, I'll pass this session to the chairperson. Okay, over to you, Dr. Wani.
Okay, thank you, Dr. Arif. And Assalamualaikum and good morning to everyone. Once again, welcome to the second day of iNUSTEC 2021. So we will start with the keynote session by the two honorable speakers, which are from South Korea and also China. And we'll start with Professor Do-jung Lee, he is one of my mentor during my thesis program back in 2019. So I can see Prof is ready here. How are you, Prof? Are you okay?
I'm good. How are you?
I'm also good. I think that first of all, I would like to say thank you very much for accepting our invitation to give this keynote speakers as a keynote speech for our event. And I hope that we can start. I think we can start our session. Is it okay?
Yes.
Before that, I would like to briefly introduce about Professor Do-jung Lee, about his major in the nuclear reactor physics, reactor core design analysis and methodology development, as well as vast research interests in nuclear engineering field, including numerical method for neutron transport and diffusion analysis, advanced reactor design, high performance computing, reactor core simulator, and others. And I can see that Prof. Do-jung Lee also has various experience as nuclear engineer in United States of America. So we are very glad to have you for today's, and I hope that all the participants can learn can get a lot from Prof. Do-jung Lee also, because he will be delivering a very good topic on the core design analysis and also methodology development. So I think just a little housekeeping for the audience. If let's say you have any question, we're going to have a Q&A session. And if you have any question, you can just write your question on the chat box. I will read it up during the Q&A session. So now, without further ado, I would like to turn time over to Prof. Do-jung Lee for your presentation. Over to you, Prof.
There is some. Okay, thanks for introduction, Dr. Ali. Let me get started. Okay, can you see my screen?
Yes, Prof. I can see your screen clearly.
Okay, it's my great pleasure to present here about the nuclear core analysis and methodology development. UNIST is a Korean university established about 10 years ago. And I started in 2011, and we developed very strong reactor physics study group. Before that, I worked in US, Oak Ridge National Laboratory, and Studsvik Power. So today I'm going to present you the two-step, state-of-the-art two-step core design tools we developed. First step is a lattice code, so transport equation, and second step is a nodal diffusion code. And if time, I know the time is limited, 30 minutes, 40 minutes, but if I have some more time, maybe I can introduce a little more about the advanced method we have been developing. So first, what is core design? What do we do for core design? We have to consider first the requirement from utility. For example, the required core power output, 1,000 megawatt electric, and how long do you want to operate the reactor? 12-month cycle, 18-month cycle, 24-month cycle. So depending on this requirement, needs of your customer, you should be able to do the design, core analysis. And you also have these limitations. Your core, your design should meet this design limit. For example, axial shape index, ASI, your core axial shape, power shape should be within certain range. Otherwise, when accident happens, your core may melt down. Okay, so same goes for the picking, FQ, this three-dimensional picking, FXY radial picking, FZ is the axial picking. And also you have to consider how to control the reactivity. So the control rod, the position is related to the controllability of your reactor core. So PDIR, power dependent insertion limit, is also another design limit. There are many such design limits exist. Like FTC, MTC, shutdown margin, critical boron concentration, etc. Excuse me, let me close my door. So what designers do is satisfy all these limits and then do the optimization of loading pattern. Your loading pattern means you have fuels, different types of, maybe 10, usually 10 different types of fuels in LWRs. And you do the optimization of the location so that you have maximum power output and longest cycle length and then lowest the peaking. Okay? That's what you do. Once you're done, then you write this nuclear design report, which include low power physics test, normal operation, and kinetics parameters, etc., which are needed for operators, power operators. And all these works is done by computer code. Okay? Computer code we use these days, not these days, from 70s, 90s, we have been using two-step code system. That's what I'm going to explain, introduce. Okay, what is two-step? What is two-step core analysis? Because core analysis, reactor core analysis include this nuclear ENDF data, okay? Evaluate nuclear data file. We use this NJ code, process this ENDF, then we get these continuous energy cross sections. And these continuous cross sections, the range of this y-axis is several orders of magnitude, so we cannot directly use it for the daily core analysis. So what we do is you solve this assembly, pure assembly, okay, with transport method, considering these very complicated cross sections. And then from that solution, we generate these two group cross sections, two group thermal group and fast group. And these two group cross sections are used for core simulation, reactor core simulation, 3D reactor core simulation. So this is two steps. First step is to generate good cross section, and second step is to do real actual core analysis. So this is called two-step core analysis. And we developed in UNIST, in my group, we developed this code stream as a first step of the two-step approach. And it solves, code solves neutron transportation. Okay, in space, we use method of characteristics, and in energy space, for resonance treatment, we use PSM. This one is we developed in our group, and very accurate and very practically fast and very accurate method for resonance treatment. So this is Boltzmann transportation. Time-dependent Boltzmann transportation and steady state to the source fission source. Total source can be some of these scattering source and fission source. We put rays like this for this pin cell problem. Inside there are fuel, and outside there is a cladding, and each region, different color, is called as flat source region. So in each region, we assume the neutron source, the sum of fission source and scattering source is that. And then we put this many rays, and for each ray, it is first order ordinary differential equation. So we can get easily get the analytical solution on this line, over this line, because it's first order and the source term is assumed to be constant. So for each track, for each pieces of lines, for each piece of these lines, we repeat the analytical solutions and accumulate the information, and we'll get the angular flux information and scalar flux information, and multiply fission cross section, then we'll get the reaction rate, which is power. Okay, and then once we have that, then we can update eigenvalue. So in that way, that's the way MOC method of characteristics of the transportation. In terms of energy, okay, energy, resonance treatment is very difficult and very complicated. And if you miss 1% here, then you will miss 1% in your final result. So instead of using the many approximations in other methods, we directly solve this continuous energy slowing down, and on top of that, we add the CPM ring-wise. Okay, ring-wise, each ring to ring collision probability plus ring-wise continuous energy slowing down. That's the way we solve this problem, and we can get very accurate solutions. This is one assembly, 15 by 15 fuel assembly depletion example. We do this assembly as 24 gadolinium BPs. So initially the reactivity is low and then increase. This is the period the gadolinium is burning, and then start to decrease. Okay? And we are comparing here the error. This is difference from the true solution from Monte Carlo. And these regions, the x-axis is fuel burnout, and this region, so about 600 ppm error, 800 ppm error. For other method, other known method, but our method, new method, PSM method, shows very good, very small error, very good accuracy, and there's no bias over the burnup. This is very important point. Our new method can handle this isotopic interference effect very accurately. So there is very small bias because of the burn-up, the fuel composition changes. Each isotope affect each other, and we handle that in our method. We handle that very accurately. So that's why we do not have much bias over the burn-up. The same thing goes for enrichment. Okay? So you can solve 1%, 2%, 5%, 10% cases. Still, if you use our method, then it will not show much bias. Small error for all enrichment. There are many things to talk about this lattice code, first step, but we have to cover the second step too. So I just put the titles here. Okay? Lattice code should be able to do this resonance treatment, method of characteristics, and critical spectrum calculation. Okay, so pure, when you solve pure independently in the environment of infinite array with the reflective boundary condition, then the eigenvalue, effective value can be 1.2, 1.3 for pure. But once you put that pure in the operational core, then because of the leakage, inward or outward leakage, we won. So there are two different spectrums. And the core is pure is loaded in the core, and the pure assembly is calculated independently. There is some, you need to do some calibration adjustment. So we need this spectrum calculation capability in that scope. We also need depletion. We use 1600. We have several versions, but for routine calculation, we use 1600 scopes with the PEM method, Chebyshev rational approximation. And then from the solutions, we produce two protection together with this assembly discontinuity factor, corner discontinuity factor, point discontinuity factor, improve the nodal calculation accuracy. The goal of this lattice code is to generate a cross-section for nodal simulator. So we have to do many cases in this case matrix. Encode detector signal. Detector signal also can be simulated. Thermal experiment. This is important for your application automatically, because all the parameter is given at the nominal condition. It is room temperature, okay, degrees Celsius. But the operation temperature is 300. So our code has capability to do this automatic summary corresponding to the operation. Maybe in this way I'll be very, very slow, so I need to speed up a little bit further. The second step is RASK-K. The code name is RASK-K. This one is nodal diffusion simulator. This is our code system: stream and RASK-K. RASK-K is diffusion solver. Stream is a transport solver, which solves pure assembly. And then Stura is the linkage code, collect the information from stream output, and then make a table, cross-section table for RASK-K. And RASK-K solve the core 3D nodal calculation, and then this is the real workforce for the core design and analysis. There are many informations, okay? Stura, the linkage code, transfer from stream to RASK-K. And this stream RASK-K is the code system we developed in iNUSTEC. But there are also other code systems: Dragon ANC, Westinghouse, Armstrong, KNF, Cosmos Simulate, to speak. This is most popular, right? Cosmos Simulate, very accurate, very efficient. Okay, RASK-K, we should use the cross sections from stream 2D calculations. So we need to do this functionalization, interpolation. And then the diffusion solver, we chose unified nodal method, unified nodal method. The advantage is there are many different methods developed for this differentiation. Nodal expansion method, analytic nodal method, AFN method. In this unified nodal method, we can choose any of them. It depends just changing by changing the options, we can choose any of them. So that's the advantage. We also have a pin-by-pin kernel, as well as this nodal, assembly nodal kernel. And inside we have our own TH solver, micro depression. And we can, the applications of this code, we did many verification and validation with the real data from real PWRs in Korea. And we further developed multi-physics coupling with this code. As they coupled with fuel performance code and core subchannel code. Okay. Also, we can apply this uncertainty quantification using this code. Also, this code has been extended. We are developing not just LWRs, we are developing this VVR, hexagonal assembly version, and fast reactor version. And maybe soon we will start to develop more MSR version of this code, MSR. We have collaboration with some company, a venture company, so we may be able to develop MSR version. So this is the application area, okay? SMR design, extrusion tolerant fuel, and the rod ejection extent analysis. We can also use it for artificial intelligence. So one of my students is developing Rust AI. So the core simulator code based on using AI based on the data generated by the real physical Rust-K. Rust-K code has real physics model diffusion, and it can simulate many different scenarios and generate the data. And in Rust AI, this code can be trained by these data, and then the advantage of this Rust AI is much faster than Rust-K. Because it doesn't have to go through all the physics calculation. It just trained by the data and produce the result. And the Rust-K can use this coupled with the subchannel CTF and then system safety analysis called Mars. And we are planning next year, we are going to couple with Cupid developed by Carib. This is a CFD code. We also developed this spent nuclear fuel package, which can give you isotopic inventory of each fuel pins at the discharge from the core, and then in the spent fuel pool in your power plant, there are many in Korea, thousands of fuel assemblies. This Rust-K SNF tool can calculate pin-wise isotopic inventory of those all assemblies, all pins. We are also developing this digital twin. Digital twin means there's a physical reactor, nuclear reactor operating today. And then we have a computer server which simulates this Rust-K as a digital twin. This is the digital copy of the real power plant. Many adaptation techniques is used to simulate as close as possible to real physical reactor. And Rust-K we are testing with the Korean nuclear power plant, Korean type nuclear power plant, OPR 1000, APR 1400. Okay. It's about the functionalization cross-section. Okay, so we need this. This cross-section is functionalized as a function of these many parameters: position, boron concentration. This data is from STEAM, the first step of the two-step of system. And this is about the diffusion solver. We use UNM, and then we use this acceleration method, and the bi-CG step as a linear solver, and also we have SPC solver. This is about internal pin-wise TH solver. This is a closed channel. So when you use this internal TH solver, it is closed channel, pin by pin, pin-wise. And then when you couple with the CTF, you can handle this cross flow. The next one is slide shows thermal conductivity model. The pure thermal conductivity, the K, the values changes depending on the burn-up, okay? Burn-up and gadolinium content, and there are many parameters. Okay? So if you look at this figure, x-axis is pure temperature, and then thermal conductivity. And we take these functions from FRACON, which is pure performance code, and then put it into RAS-K. So RAS-K thermal conductivity model is equivalent to FRACON thermal conductivity model. So which is more accurate than the usual case. Usual case just constant value over the burn-up, but over the burn-up it changes. For example, like this gap conductance, it increases initially and start to decrease once the pellet and clad, the mechanical, okay, the contact occurs, and then it changes. So very complicated thermal mechanical properties. So we are using those properties from FRACON code. It is well validated. And this shows the micro depletion chain, 22 heavy nuclei and 12 fission product, and vulnerable observers, gadolinium chain, and xenon, samarium, okay, xenon oxidation to model. There are more engineering features. For multi-cycle, cycle 1, cycle 2, cycle multi-cycle modeling capability, we need to have this start from some file, save the file from the previous cycle. Each assembly, once you simulate one cycle, each assembly information goes to binary file. And when you start a new cycle and plot one cycle, you read those information back into start capability and jumping capability, folding, unfolding, and shuffling rotation. These are all needed for the real reactor simulation. Also such options, okay. Critical boron concentration. You want your reactor operate at the condition. So what PM the reactor will be RAS-K code as this capability. Also critical control position, or you can use not just critical, okay, you can use different target K value as a user input. Also cycle length search, okay, 10 ppm. You start from 1500 ppm at the beginning of cycle, and you operate 16 months, 18 months. Then the boron concentration becomes 10 ppm. Then point you need and also mass flow rate search. This is additional capability to match the inlet outlet temperature. There are many other things I cannot go through all these, but peak power reconstruction, okay? Because use this nodal solver, use this assembly size node calculational mesh. So, but for real analysis, reactor safety analysis, you need pin-wise power. From this assembly power, you need to reconstruct pin-wise power. So this additional module you need the nodal core. For reactor analysis, you need also many branch calculations, like pure temperature coefficient, moderate temperature coefficient, many parameters. Then many core design parameter, okay, printing capability, picking factors, rad was, xenon summary was, and also boron. In the coolant, boron, okay, during the operation, boron, the concentration, boron content, boron 10 deplete, boron 10 absorb neutrons, boron 11 doesn't. So the composition, the isotopic fraction changes. So we have that the tracking capability of this boron fraction. Also in core detector signal generation, we use SPND, cell powered neutron detector. As an emitter material, we can model vanadium, rhodium, cobalt to silver, okay, and also movable detectors. We can also simulate that and generate detector signals and DMBRs. And between the cycles, there are pooling period, overall period. Okay, remove the bond fuels and reload the fuels. It can be 2 months, it can be 4 months, it can be 6 months, depending on situations. Then during that time, the radioactive isotopes, they decrease. So we should be able to model it. And for safety analysis, this RAS-K also has interface capability with the system called Mars. Mars is Korean version RELAP, okay, Korean version RELAP, the safety analysis code. So for local analysis, RAS-K can provide these informations, kinetics parameters, picking factors, FQR, delayed neutron fraction, and the constant. I'm sorry, someone said something.
Sorry, Prof. Probably the participant does not mute his microphone. So we will.
I'm sorry. So
no, there's nothing because I think the participant forget to unmute his microphone.
Okay. Sorry. Then I have about 8 more minutes, so I'm going to finish up, speed up and finish. Okay, this page shows the interface. RAS-K produce interface with the fuel performance code, FRAC1 and FRAC-TRAN. Okay, these are the data from RAS-K to fuel for multiphysics analysis. This is about detector signal, and this is about the source pump. This is very important now in Korea. Okay, the first nuclear power plant in Korea, Gori Unit 1, was determined to decommission. Okay, was determined to decommission soon. And to decide when to start the decommissioning, this isotopic inventory, the radioactivity in the fuel, okay, fuel in the spent fuel pool, very important information. And there is no measurement for that. Okay. So it's very important to simulate or calculate those kind of information. That's what utility need before starting the commissioning. So we have that capability. We have implemented that capability, and the accuracy is around here, okay, within 1%. It's very good accuracy. This is very important capability for the company. And we have also added this crowd modeling. Once you operate about 10 years, then you start to see these borons inside the plant start to deposit to the pure rock, outside pure rock, the top of the core. So it has effect to the axial power shape like this. This axial power index, axial shape index. This blue line is the normal case. And this line, black line, is the case when you have crowd in your reactor. So they are very much different. Okay, so it's outside the design. Could be outside design boundaries. So you do not want to do this. Okay, you do not want to operate your reactor like this. So the first step is to be able to simulate this phenomenon. So this red box, okay, the scale is the one calculated from our code. It's very important and very good. So this shows the calculation result. The top part, okay, the top part of this, the red one shows the cloud material. Okay, pros, cons. Last K compared to other code, there are many pros. Okay, many advantages. Very flexible, the solution kernel, UNM, Unified Nodal Method, and micro depletion. The traditional old, the other code, most of them use macro depletion, which is less accurate, which has to use this spectral index kind of things. We do not need that because we can handle this micro depletion. And many different types of this controller. Okay. For VMV, we have been doing this for many cycles, many reactors, but I'm sorry, I cannot present this. I cannot show this because of this proprietary information. But what I can say is we are using ENDF 7.1 and gender, and depletion also 7.1 gender, and then we chose this physics model, uranium-238 upscattering and expansion and OT. These are also very good capabilities of this code. There are many small things which also, even if it is small, they are small, still we need them to improve the accuracy, reasonable accuracy. I'm going to skip this one. And there is advanced features. We are developing RASK version 2, 3, and Stream can also directly use to the 3D core analysis and Monte Carlo code. And we are doing coupling with this thermal hydraulic code and fuel performance code. So some of them are finished, some of them are on the way. So we are still continuing the development. So there are some advantages by doing the multi-bit coupling, for example, like this prep-on-prep-on. This is how we couple this, but due to time limit, let me skip to some results, some movies, some simulations. Right. This is the case I want to show. So this is coupled case, last case, subchannel and prep-tran, pure performance, multi-bit coupled, rod ejection extent. So this is the algorithm how to solve. This is the power shape we are expecting. Start from 0 power, and then it increase because of the control rod is ejected. Okay, the positive reactivity is inserted, power increase, and then temperature also increase, and then by the Doppler feedback, the temperature goes down again. Simulation. Let me show you this. This is the movie, okay, showing the simulation. We start from 0 second. Does not show the time. So there is a power peak, total power peak. This is the core. The control rod was ejected at this point. So it can be like this, and then because of the Doppler feedback, it comes down. And we can, because of this multiphysics, we can take a look at other parameters too. Okay, enthalpy rise, linear power, reactivity, and axial elongation, hoop stress and strain, fuel temperature, cladding temperature, and gap conductance. Okay, so we can do very detailed analysis of this dejection extent, and probably I'm going to stop here. Okay. So we developed very good code system, the two step, the transport and diffusion, and we coupled with other physics, thermohydraulics, and pure performance. And then we are doing verification and validation. And for advanced features, we also develop direct analysis, stream 3D version, direct analysis of the whole core, and then Monte Carlo whole core analysis core system. So maybe I can introduce both things when I have another things. Okay, that's all from my side. It's 10:40. Okay, thank you for your attention. Any questions for me?
Thank you, Prof, for your presentation. So for now, we still have 5 minute time because we start late at 5:95 just now. So probably if there is anyone who would like to ask Prof. Dr. Julie question, you can unmute your mic and ask him. Because I think his topic today is very interesting regarding the core development.
Good morning, Prof. Lee.
Yes.
So I have one question, maybe just a little bit short one. So regarding this, the RASK code, is there a possibility that we UTM can calibrate or to use the code or anything that we can work on with the code of the RASK, or is it just for internal use only?
It's not it's not, there's no limitation actually, depending on the arrangement, your organization and my lab and my university, we can share this code with you guys. But well, there is no the policy yet, okay, fixed policy about how currently we are using this code in our lab, and then several other universities in Korea, and also KHMP, the company, okay, utility company also using it. And now we are talking to the regulatory. We started talking to regulatory, Korean regulatory, so that they may be interested in using this code for their regulation reviewing work, okay? And outside the country, there is no plan yet. There is no, I mean, no plan means we are not going to share it with the outside. That's not the, that's, well, we have not decided yet, okay? That's the correct way. We have not decided yet sharing this code with the outside. So if you are interested, send me email and we can discuss further, okay?
Okay. Thank you so much, Prof. Dajali, regarding your keynote speech. It's very insightful and quite interesting topic especially for the nuclear engineers who working in this core design and analysis. Once again, I would like to say thank you so much, Prof. Dajali. And if let's say we can talk more, we can send email for sharing session and so on.
Yeah,
Thank you,
sure.
Prof. All right. Have a good day.
Okay, thanks for having me. Bye.
All right, thank you. But we're going to proceed with the next keynote speech that will be delivered by Mr. Ding Jiang. He is the Vice President of China National Nuclear Corporation, CNNC, China Zhongyuan Engineering Corporation. So I can see Mr. Din Jiang is here already. So before we
Here.
yeah, I can see you. How are you?
Okay, fine, thank you.
All right. So before we start, I would like to
I need to unshare.
Prof. Dr. Julie, you need to stop sharing your slide for now. Okay. Thank you, Prof. Dr. Julie.
You're welcome. Thank you.
Okay. So we're going to proceed with the next keynote speech by Mr. Din Jiang. So a brief about he is born in 1966. Din Jiang completed his study on thermodynamics in 1988 and graduated from Zhejiang Universities. He worked on NPP design and engineering for decades at CNNC China Nuclear Power Engineering Corporation. In the latest year, he is a vice president of CNNC or CZEC, which is the unique platform of CNNC for International Nuclear Corporation. And Mr. Din Jiang is taking charge of global market development. So without further ado, I would like to invite Mr. Din Jiang to deliver his keynote speech entitled of Nuclear Engineering, First Overseas HPR 1000 Project. Over to you, Mr. Din Jiang.
Okay. Thank you. Good morning. Friends, that my name is Ding Jian. I'm the vice president of the DEC of CNNC. And my great pleasure to join you. Can you hear me?
Yes, I can hear you clearly, but I can see that you start sharing your slide, but there is nothing showing.
The slides?
For now, we just see blank. We don't see any slide yet. So probably you can just stop sharing and share it again.
Or
Okay, now we can see it clearly. Sorry, Mr. Ding. If you talk anything, we cannot hear you from here. So are you okay over there?
we said today, right now we are waiting for the screen.
Okay, now I can hear you and I can see you as well.
So it's some- no.
Probably we wait for a while. You share something, but we cannot see anything. It's just a black. Probably you can stop sharing and share it again. Okay, now we can see it.
Okay.
All right.
Sorry to keep you waiting. So, it's really my. It's okay now.
Yes,
Okay.
we can see it.
Hey, sorry.
All right.
Okay. The 2021 Nuclear Science, Technology, and Engineering Conference online have introduced the HPR1000 technology, and it's the first unit overseas. So on behalf of CNNC and the CDEC, I'd like to extend my warm congratulations on the successful convening of the conference, and heartfelt thanks to friends from all walks of life who have been long committed to promoting Sino-Malaysia and the China ASEAN Nuclear Energy Corporation. So to begin with, please allow me to brief you some on Indonesia, as well as the recent nuclear energy cooperation between Indonesia and Malaysia. Indonesia is one of the few large state-owned enterprises in the world to boast a complete nuclear industry chain, and has earned itself a position in the Fortune Global 500 in 2021, and it's the only nuclear enterprises in the world can be into this list. So over the past 60 years, Indonesia has established an industrial system featuring
Once again, sorry, Mr. Ding. We cannot hear you. Once again, sorry. Probably the internet connection is not good this morning. So please bear with us a moment while we try to hear from Mr. Ding again.
Hello?
Hello, yeah. Are you there?
Okay, it's okay. Okay,
All right.
I just want go ahead. So over the past 60 years, CNNC has established the industrial system featuring 9 core industries. So I have explained that advanced nuclear energy utilization, nuclear fuel, natural uranium, nuclear technology application, engineering and construction, nuclear environmental protection, equipment manufacturing, and renewable energy, and financial investment. So a series of homegrown nuclear power technologies has been developed by CNNC. You can see that in the slides, on the slides.
I'm sorry, Mr. Ding, for interruption, but we cannot see any slide now.
Oh, so that means we cannot share video and audio simultaneously, right?
Or maybe you can use another device to share the screen only.
Okay.
You use your phone for
Yeah.
audio and video.
Maybe 你这个好像也快没电了，要不然这样子的吧，我先就干脆就说，到时候让人把 PPT 给他们。Sorry, I propose that I can just speak our content, and later on we can send the our PPT to everybody. Is that okay to save the time?
Okay, sure. But maybe you can ask your friends to email to me your slide, then we can share via here.
Okay. 哦，你传给他行不行？ Okay, may I go on to speak?
Sure. You can.
Okay, great. Thank you. So that's CNNC. So generation 3, HPR 1000 and ACP 100, and also we have generation 4 technology, high temperature gas cooled reactor. So CZEC is a platform wholly owned by CNNC to specialize in CNNC's complete industry chain.
Sorry again, but we lost your voice right now.
Okay.
We hear echo.
It's okay right now?
Yes.
Okay.
Okay, sorry. Okay. So today I like to share you some experience in the construction of the first HPR 1000 project overseas. Namely, and now it's we call that the Karachi 2 and 3 project, to share our experience of the construction. So HPR 1000 is generation 3 technology. So based on the China's more than 30 years of experience in the nuclear power research, design, manufacturing, construction, and operation. Meeting the most advanced regulations and safety standards in the world, HPR 1000 has three major technological characteristics. First, the technology is advanced and mature. It adopts the world's highest requirements for safety and the latest standards for technology. The technology satisfies the safety requirements of the International Atomic Energy Agency, IAEA, as well as American and European standards for Generation 3 technology. Second, it's safe and economic. Practical and effective measures have been taken to improve the unit safety from its top-level design and incorporate the feedback of Fukushima accident. Thirdly, it combines active and passive features, and HPR 1000 has adopted the effective passive safety measures on the basis of active safety. So, and it's one of the Generation 3 technology with the highest acceptance in the current nuclear power sectors. So the demonstration project, Unit 5 in Fuqing Nuclear Power Plant, has been in stable operation for 254 days after its commercial operation, and the first overseas project is 142 days. So it's an example. So to build the first HPR 1000 unit overseas has never been an effortless job. So especially when the challenging installation of main equipment takes a long time and is subject to high requirements. Back to when the construction started, no power plants with HPR 1000 technology are completed as a reference. So coupled with risk, unlike those of domestic construction, we faced more difficulties in Pakistan. So great uncertainties surrounded the on-time completion of the project. Many in our industry reckoned it's an impossible task. However, since the project commenced, its construction has been steadily advanced with its safety, quality, schedule, and cost fully under control. So on May 20th this year, the first HPR 1000 units overseas, Karachi Unit 2, achieved the commercial operation. Unit 3 is scheduled for initial fuel loading by the end of this year and the commercial operation in April next year. So the successful completion of the first overseas HPR 1000 unit could be attributed to the following points. The first one is the practical experience condensing into overseas project management model. CZEC has been learned from its engineering practice of nearly 40 years, encouraging innovation, and came up with a complete project management system. So during the construction, CZEC emphasized on-site construction, headquarters support, and on-site headquarters collaboration by making it a project operation model. Against the ravaging pandemic, CZEC as a general contractor has been shouldering full responsibility and strictly implementing pandemic prevention measures on site. Meanwhile, with a systematic thinking approach, it has been pulling on-site resources, coordinating domestic and foreign resources to advance the construction. So responsive procurement, equipment procurement mechanisms, including flexible and diversified ways, such as video links to accept the key equipment, and continued innovation in engineering method has improved the efficiency in eventually shortening the construction period. After the discouraging pandemic, SEDEC still managed to build Unit 2 and 3 in Karachi with similar construction period with reference units, Fuchin 5 and 6, only 69 months from the FCD to commercial operation for the Unit 2. So we have the achievement. Such length sets the record of the shortest construction period for the first unit of Generation 3 technologies to be constructed overseas. The second one is innovation in construction technologies enhance core competitiveness. So SEDEC, the technological innovation is a major boost to nuclear project construction and the enterprises development, and the greatest vitality of technological innovation just lies in the front line of nuclear project construction. Multiple factors on the project side have made construction period the highest risk for overseas project. Taking into consideration the natural environment, infrastructure, economic development of Pakistan, SEDEC upheld the principle underscoring inclusiveness, facts, bold ideas, and verification on its way to innovate the construction techniques. So there's successful innovations in the introduction of main equipment, including modular building for reactor cavity pool, integral hoisting of polar crane, pre-introduction of pressure vessel and steam generator, and E-type flip bracket, and pre-stressed double platform construction have ensured that the installation of main equipment starts in advance. Take the pre-introduction of main equipment as an example, as civil engineering and the instruction and the installation are advanced together. The installation of main equipment and the main pipeline welding started 7 months ahead. After those, the EC no longer follows others, as it has become a leader in relevant fields. Now that SEDEC's competitiveness continues to grow, the economical features and international competitiveness of HPR 1000 technology will also be strengthened, and its economic, social benefits, and wide application prospects be proved. The third one is strengthened safety management improves performance of overseas project. SEDEC has high standards and strict requirements for project construction and believes that all accidents can be prevented. During the construction of the first HPR 1000 project overseas, drawing on advanced HSE management experience from domestic and foreign counterparts, and accommodating the fact that HPR 1000 units are built overseas in Pakistan, CDEC has developed a set of safety production management philosophy and methods to suit Pakistan's conditions. Between commencement of September 2021, K2, K3 project has set a record of zero accident production for over 2,700, more than 2,700 straight days, which has reached the leading level in nuclear power construction. Its safety performance has also surpassed that of the domestic nuclear power construction project in the same period. The TRIR of 0.26 has become a benchmark in the nuclear power industry around the world, which further indicates that CZEC's safety management for overseas nuclear power project is on par with that of leading engineering enterprises in the world. The fourth one is the strict quality control gives rise to the project of excellence overseas. So quality is the life of a nuclear power plant, and the construction quality lays the foundation for the nuclear safety during operation. So by the September 2021, the first acceptance rate of quality control point for construction and installation is much higher than the planned target of 95%. Since the start of construction, no conformity on site, and project quality is well under control. So CZEC has set an even more ambitious goal to our construction. The fifth one is sharing, and win-win cooperation ensures the safe operation of power plant after handover. CZEC follows the principles of extensive consultation, joint contribution, and shared benefit by building satisfying projects, while teaching project management knowledge and professional skills to local employees to the last extent. During construction, CDEC has trained more than 50,000 Pakistan employees and brought some excellent employees to China for study, exchange, and practice. So with the Pakistan employees participating in every part of construction and project management, CDEC has trained abundant management and technical personnel for Pakistan. So each HPR 1000 unit in Karachi generating around 9 billion kilowatt-hour of electricity annually, enough to provide electricity for over 4 million local households. Such yearly generation could reduce standard coal consumption by 3.12 million tons, or carbon dioxide emission by 8.16 million tons, equivalent to 70 million trees, and thus will help Pakistan optimize its energy mix and step up global efforts to deliver carbon peak and carbon neutrality. So, and moreover, I think that thanks to the procurement of local raw materials and equipment, the project has created over 40,000 jobs opportunities indirectly through the local industry chain. So therefore largely catalyzing the development of people's the well-being and the local economy. So the nuclear power is critical in our way to achieve green development, secure natural energy supply, and economic growth. In the face of COVID-19, nuclear power can be better ensure stable nuclear supply, develop related industries and upstream and downstream, and expedite the post-COVID economic recovery. So CDEC would like to share our experience and achievements in nuclear power development with Malaysia and other Asian countries. CDEC is willing to join hands with Malaysia and other Asian countries to continue to promote the safe, innovative, coordinate, and open development of nuclear energy, so as to bring more benefits of nuclear energy to the people and our society. So that's all for my sharing of the construction period experience of our overseas project K2 and K3. And thank you.
Okay, thank you so much, Mr. Ding Jian, for your sharing on this keynote session. So for now, I would like to open the floor for any question regarding the Mr. All right, so we have one question from Dr. Hassan here. Mr. Jian, thank you for your presentation. How severe is the seismic activity at Karachi, and how the HPR 1000 copes with such condition?
Okay. Excuse me, could you repeat the question?
Okay, the question is, how severe is the seismic activity at Karachi, and how the HPR 1000 copes with such condition?
You mean the severe conditions, the natural conditions in Karachi?
The seismic activities.
Didn't. Okay. Seismic, I think that is you know that the HPR 1000 is generation 3. So we can meet the seismic, it's 0.3G. We can meet the target. So nowadays in Karachi is 0.25. So that is okay for us, the HPR 1000, to meet the requirement. And also in China, most of the sites all over China is less than 0.3G. So right now it's no problem. And also for HPR 1000, if some site can more than the seismic level, more than 0.3G, also for us, we can improve our design and make it localized to meet the requirement. That's the answer.
I see. So I believe that because of the HPR 1000 is Gen 3 reactor, so it can help in terms of all those restrictions in terms of seismic activities and so on. So I can see here Mr. Suhaimi raised hand. Do you have any question to Mr. Jiang? Dr. Suhaimi.
No.
Okay, good morning.
Yeah.
Yeah, I'm Nahul from UTM. Thank you for the interesting presentation. So my question is that what is the difference in construction time between overseas project and the domestic project for you? Is there any difference at all? Yes.
Yes, for the demonstration project, the domestic one started from the May 20, 2015. And also for the overseas, it's 3 months later than the domestic one. And also for the construction period. So only for the domestic one is only 2 months shorter than the overseas one.
I see. Why is that the overseas one take longer than the? What is the main factor that make the overseas construction longer than the domestic one?
Okay, so the factor is, you know that in Pakistan, so the conditions is I think that it's quite poor than that in China. For example, the poor security, the underdeveloped industry, and the time-consuming transportation, and inadequate workforce. And also the biggest one right now is for the pandemic, for the COVID-19. So for the prevention of this in Pakistan, it takes us at least 2.5 months to prevent that.
I see.
So that's why we have a longer period than the domestic one.
Okay, just last one from me is that you mentioned earlier about modularity. So how much is the use of modularity or modular system reduce the construction time overall compared to? Okay.
Yes. So we adopt a lot of innovative methods to make it shorter. But I think that for the pre-introduction and some methods, but even under that condition, so even under this, we still have some delay, or we have some gaps between the domestic one and the overseas one. That's because the previous I have mentioned that some factors because of the equipment and the workforce and the some local industries, a lot of things.
I'm sorry, I thought I have a last question, but just now. But I have just one more, Mr. Jan. Is that is the construction time different for different types of reactors, or they are about the same?
That means different types have different construction period, right?
Oh, I see.
Yes. Nowadays, I've mentioned that in Sinanense we have a series of products, the HPR 1000, ACP 100, and the HTR, something like that. I think that different types of technologies have different kind of period. For example, HPR 1000 has a large amount of concrete and a large amount of installation work, so it will take longer. But if for example, for the small modular reactor, it could be much shorter, maybe 48 months, something like that.
I see. Okay. Thank you so much. Thank you.
Thank you.
Good morning.
Yeah.
Mr. Jan? Yeah. This is Jasmine from UTM.
Okay. Yeah.
I just wanted to know whether when you are building power plant overseas, do you bring I mean all the labors and so on from China, or you use the local people, and in such a way we can have I mean some sort of technology transfer to the local people as well.
Okay. I think that depends. It depends on the infrastructure and the base. I think that some conditions in which country. I think that maybe I think that in Malaysia, that is quite no problem. For other, you have the higher and also very strong infrastructure, and you have a lot of manpowers, man forces, workforces. So for us, first one, we will comply with the local law. If you have the law, so we will make our full use of the local resources. For example, for the consultation, the supply chain, and also local workers, laborers, and the local any local resources to the most of the extent. So that's no problem. We can only bring some the technical persons related to their construction and also the installation, something like that, for consultation. Just for that, not bring our laborers from China to Malaysia and also other countries. So we can guarantee and promise make full use of the local resources. We don't have to.
Okay, thank you.
Yeah.
Yeah, may I? I'm sorry if I want to ask one more question. That for this construction in Pakistan, for example, what is the local content percentage-wise?
Okay, so that's different. That's different. You know that we have already built 6 units in Pakistan from the Chashma 1 to 4 and the Karachi 3 and 2 and 3. Yeah. So from the very first one up to now, the local content is getting more and more. So for the Karachi 3 and 2 and 3, I forget the total money, the price of the project, but I know that we have a lot of the local supply of the containers and local materials, and also the local laborers, more than 10,000. And also we have the local services firms to combine in, and I think they and also have some small EPC. For example, the water purification plant and also the demineralizing plant are also submit. Also we they offered to the local contractors. It's much more than the Chashma 1 to 4.
I see. Okay, thank you again.
Okay.
Okay, I think with that, is there any ask question from the floor? Okay, I think really I think that's all that we can say from the audience, and thank you so much again for Mr. Ding Jiang for your presentation about this HPR 1000. It's very nice to see this kind of development and so on. All right.
Okay, thank you so much for your listening.
All right, and I think we can wrap up this session for today's. So thank you everyone for attending this session. So we're going to moving on to our next schedule. So we're going to have the following session is the paper presentation session from the participant with the teams of materials and sustainability team. So and this session will be chaired by Dr. Arif. So Once again, thank you for both of our distinguished speakers for this keynote session. And with that, I would like to pass this screen to Dr. Arif for chairing the next session on the paper presentation. Over to you, Dr. Arif.
Thank you.
Okay, thank you, Dr. Sazwani. So I'll be chairing this paper presentation session for materials and sustainability. So if we look at the schedule, the first one should be from Dr. Sofian, but when I see back the registration, I see that this title is supposed to be a poster presentation. I mean, a poster submission. So I see Dr. Sofian is here. Is it? I mean, are you going to present, or because it's my mistake, because I thought this is a oral presentation, but it's supposed to be a poster.
It's okay, Dr. Arif. If you want me to present, I will present. If not, okay, it's okay also.
Do you want to present? Maybe you can just proceed with the presentation.
Since I'm here, maybe I can do a short presentation of my paper.
Okay,
Dr.
sure.
Arif?
Yes, that should be good.
May I start now, Dr. Arif?
Yes, you can start now.
Okay. Assalamualaikum and salam sejahtera. My name is Sofian, and on behalf of my research team, I will present our research finding on mechanical properties and thermogravimetric analysis of peroxide pre-vulcanized natural rubber latex induced by cobalt-60 gamma radiation. So this is my presentation outline today, where it will cover introduction to natural rubber latex and vulcanization process, and then problem statement and research objective. This presentation also will share on materials and method that we are using to run this study, and also results and conclusion from this study. So ladies and gentlemen, research and development in latex technology are one of Malaysia's main priority. For example, at 2019, sales for glove alone contribute almost 23.5 billion to Malaysia income, and these figures expected to keep increasing every year. So we hope this new generation latex can help to generate more income for Malaysia in the future and support economic transformation project launched by the government a few years back, where one of the entry point project in ETP is a commercialization of new generation latex. So what is natural rubber latex? Natural rubber latex or polyisoprene naturally exists in white liquid form, sticky and non-elastic. In order to tackle this weakness, latex need to be modified through process named vulcanization or crosslink. Through this vulcanization process, latex will become more elastic and heat stable. Generally, there are three popular vulcanization process, which is sulfur, gamma, and peroxides. Shown in the slide is a preparation of pre-vulcanized natural rubber latex through conventional sulfur vulcanization process, which was found by Goodyear at 1844. In this process, besides sulfur, other chemicals such as zinc oxide and dithiocarbamate will be used as activator and accelerator inside the latex formulation. Then, the formulation heated at temperature 65 degrees centigrade for 10 hours. For your information, chemicals such as zinc oxide and dithiocarbamate is carcinogenic substances and can cause cancer and also potentially cause type 1 and type 4 allergies. If we don't use this chemical in this conventional process, the vulcanization process will take a longer time and need higher temperature. So it's not good for latex industry. The peroxide vulcanization of natural rubber latex was introduced by the Malaysian Rubber Board since the early 1990s. In conventional peroxide vulcanization, organic peroxide will be mixed with natural rubber latex and activators such as tetraethylene pentamine and fructose before heated at 70 degrees centigrade to produce pre-vulcanized natural rubber latex with tensile strength of approximately 18 to 20 megapascal. The function of these activators is to yield free radicals from peroxide to promote the formation of rubber chains cross-linking. Whereas without the presence of this activator, the cross-link reaction of the natural rubber latex will occur at very low rate. Unlike the radiation pre-vulcanized natural rubber latex or RVNRL that was introduced by the Malaysian Nuclear Agency, peroxide vulcanization also faced the same problem, which is it produced a low tensile strength films. This made it unsuitable to be used in the production of premium latex products such as surgical glove. Moreover, there are some cases where the use of activators in peroxide vulcanization tends to produce natural rubber film with darkened color during the drying process. So the reason that why we want to find another process and new generation of pre-vulcanized natural rubber latex is because, firstly, there are some cases where the use of activators in peroxide vulcanization tends to produce natural rubber latex film with darkened color during the drying process. This will make the product look less attractive to the customer. In addition, based on our previous study, it is possible to cross-link or pre-vulcanize natural rubber latex without activators and coagent in peroxide vulcanization, whereas the high radiation energy from gamma capable to promote the peroxide decomposition in natural rubber latex for the formation of rubber chains cross-linking. So based on the problem statement that I've mentioned before, our research team agreed to set this objective for our study. So our first objective is to study the optimal radiation doses for vulcanization of natural rubber latex via peroxide vulcanization, which is based on its mechanical properties or tensile strength of the films. Then our second objective for this study is to study the effects of radiation on cross-linking density and thermal stability of the peroxide vulcanization natural rubber latex films. The latex utilized in this work is ammonia type supplied by Rivertex Malaysia. The peroxide used were third butyl hydroperoxide supplied by Fluka Switzerland, and the stabilizer used was potassium laurate supplied by Tiaco Chemical Malaysia. And lastly, antioxidant used was Equinox LP supplied by Aquas Persian Malaysia. All these material were used as received. So pada slide ini tunjukkan formulation to produce 6 kg new generation peroxide pre-vulcanized natural rubber latex. In this process, chemicals such as peroxide, stabilizer, and water were first prepared into an emulsion before slowly added into the latex with gentle stirring. Once the addition of the emulsified materials was complete, the latex mixture will left stirring for 3 hours. It was then transferred into 6 separated 1 liter screw cap plastic container and irradiated with gamma rays from Cobalt 60 source at Mintek Sinagama plant at varying dose of 0, 5, 10, 15, 20, and 25 kg respectively. After radiation, the latex was made into film by coagulant dipping method to measure its mechanical properties, gel content, and TGA and differential thermal analysis. Based on our previous study, the activator and coagent in peroxide vulcanization are no longer needed when using gamma radiation because high radiation energy from minus radiation capable to promote the peroxide decomposition in natural rubber latex for the formation of rubber chains cross-linking. For this study, the optimum radiation doses for vulcanization of natural rubber latex via peroxide vulcanization system are determined based on the tensile strength of the films. This is because parameters such as tensile strength and modulus values are very important in the production of latex dip product. and some products have to meet certain standards. For example, the minimum tensile strength to produce examination glove is 18 megapascal as required by the STM D3578. Table 2 gives the mechanical properties of PVNRL samples that have been prepared by gamma radiation at various doses and tested as required by STM D412 standard. The increasing of the tensile strength of the PVNRL is suggested due to the increasing of the intraparticle crosslink density or chemical crosslinking caused from the increasing radiation dose, which lead to the formation of a three-dimensional network of all rubber matrix. Besides, the interparticle entanglement or physical cross-linking also suggested to increase with the increasing dose because of the interparticle entanglements depending on the free rubber chains end at the surface of each lattice particle, whereby these chains interpenetrate during film formation and contribute to the strength of the film by means of entanglements. The gel content or percentage of cross-linking is determined based on STM D3616 requirement. The effect of radiation doses on gel content of PVNRL are shown in graph. From the graph, it was observed that the extent of gel formation increased with the increasing of radiation dose, indicating increase in cross-link density of the polymer. At 25 kg of radiation dose, PVNRL film produced 84.5% cross-link percentage compared to the control sample at 35.9%. TGA analytical technique was used to determine material thermal stability for PVNRL that was prepared at various radiation doses. When natural rubber latex are cross-linked by peroxide and radiation, carbon-carbon bond are formed between individual rubber chains. And for your information, the carbon-carbon bond is stronger and more thermal stable than the carbon-sulfur bond formed by sulfur vulcanization. So from the TGA analysis that was conducted on all PVNRL samples, it was observed that the weight loss of the PVNRL samples occur at the temperature range of 300 to 540 degrees centigrade, corresponding to a degradation of the non-volatile residues. Besides, T degradation for the sample are around 378 degrees centigrade. From the weight loss curve, a clearer picture of the effect of radiation doses on the thermal stability of the latex has been observed. The thermogram clearly shows a less steep gradient for the entire PVNRL sample that was prepared from 5 to 25 kg compared to the control, which is 0 kg. These results were attributed to an enhancement of the carbon-carbon crosslink density of PVNRL as consequence of the dose effect, whereas increasing of the carbon-carbon bond density also increased the thermal stability of the latex. So as a conclusion, peroxide pre-vulcanized natural rubber latex, with promising high tensile strength, can be prepared by induced with cobalt-60 gamma radiation. Latex formation based on 0.1 pphr of BHPO and 0.06 pphr of potassium laurate as stabilizer at radiation dose of 25 kg can produce rubber film with tensile strength of 20.7 megapascal and crosslink percentage of 84.5%. For acknowledgement, the author would like to thank the Remediate Plant Malaysia Nuclear Agency for funding and technically support of this work. And also, we would like to give our sincere thank you to Rivertex Sdn Malaysia for supplying HL latex to be used in this research. With that, thank you.
Okay, thank you, Dr. Sophian, for the presentation. So we would like to open the floor for the question. So if you can Oh, you written off the slide. Okay. You can see in the chat we have one question. So is the PVNRL tend to accumulate after the radiation effect? Do you have any characterization or instrumentation that prove that the cross-linking process occurred in the PVNRL sample?
Thank you for the question. After radiation, the latex, we measure the latex as required by all the standard latex standard. For your information, all the standard were made all the properties, all the physical and mechanical properties of the latex is required, is achieved. All the standard are required for the latex. So for characterization, so that prove our we use what we call gel content method to which is to measure the cross-linking density.
Okay, I hope that answer the question for Dr. Amira. And that question comes from Dr. Amira from UTHM. Okay, any other question? Oh, from Dr. Leo. Do you have the info on the radiation source used in this study?
We use cobalt 60 from Sinagama, Dr. Leo.
How about the activity? The activity to get that 25 kilogray?
I mean the activity of the radiation. The activity for Sinagama at that time is, let me check out my paper. The activity is 348,778 curie, with dose rate of 1.61 kilogram per hour.
This is very high. Eh?
Yeah, very high. So it's for 25 kilogram, it takes us around 12.5 hours to finish it, the radiation.
Okay, so I hope that answered Dr. Leo's question. So regarding the result and discussion I see earlier, what does it mean by the, if you can open the slide again, at the result and discussion? I'm sorry for not, I'm not familiar with the terms previously. The first slide on result and discussion. Okay, now over here, like in the table, you say that modulus at 500%. What does it mean by the 500%?
From the standard we use, we have to this film we have to make like mold, like a dumbbell shape. Then we use one machine, ATM machine, UTM machine, utilized tensile machine, universal tensile machine. That then the machine will pull the films to around elongation more than 500%. Until it's snatched. So we then at 500% we take the measure we take the measurement. 700% also we take the measurement, and lastly the tensile strength we can get after the sample snatch.
Okay, so this 500% is based on what?
Based on the standard, Dr. Arif.
Okay.
Yeah.
Okay, so
I think what is meant is that 100% or 100% is how long it stretches, isn't it?
Yeah, Dr. Narul, right, Dr. Narul, betul.
It's how long it is stretching, because when you put it up, it will stretch maybe twice, 3 times, or 500%, and things like that. Yeah. So at that particular point, what is the reading? Yeah, that is what is saying, I think. Yeah. Right?
Yeah, at the end for industry, they want you they only use they only concern on the tensile strength. So for your information, like for examination glove, I give you earlier the tensile strength for examination glove is 18 megapascal. If you don't meet this 18 megapascal, you cannot use this latex to produce this examination glove. For surgical glove, it need a higher tensile strength compared to this examination glove. So for information, for surgical glove, we have to meet 24 megapascal of tensile strength. So for this time being, we have done some experiment to achieve this, and when already success, maybe we can present another seminar. Thank you.
Okay. We have another question from Dr. Leo. Instead of photon, do you think that we can use electron or ion beam irradiation for this application?
Yes, we can, Dr. Deo. But for your information, based on our previous study, let's say if you're using cobalt 60 or gamma radiation for cobalt 60 to get, let's say we rate 12 kilogray to produce RVNL using this cobalt 60. But if you want to using electron beam, we have to use a higher dose, because the penetration wise is for electron beam is very low compared to cobalt 60. I think for electron beam at Malaysian Nuclear Agency, previously I think maybe around, if correct me if I not mistaken, around maybe 1 cm or 3 cm penetration in water.
Oh, sorry. We are the last question. Does the modulus represent the Young modulus of the sample?
I think so, Dr. Amira, because I'm not very, I'm not very familiar with the modulus. We just get it from the machine.
Okay. So I hope that answered the question from Dr. Amira. Okay. So I think we will close the Q&A session. So thank you, Dr. Sofian,
Thank you,
for
sir.
the presentation on the poster. Okay. So we hope to see you again in the next conference.
Inshallah. Thank you, sir.
Okay, so let's proceed to the next oral presentation. So the next the title is Physical Properties of Polyvinyl Alcohol Gel Materials as Phantoms for Mammography. So I see Dr. Muhammad Yusof is here. Okay, so are you ready?
Yes, I am. Okay,
Okay.
Assalamualaikum, everybody. Okay, so I would like to present my study on the physical properties of the physical properties of polyvinyl alcohol or PVAL gel material as phantom for mammography. So this is one of the study from my group of researchers that consists of our graduate students and also several other contributors. Okay, so firstly, the phantom material is a very common tool in medical physics works because usually we use phantom to simulate the properties of human soft tissues in terms of attenuation of the radiation. So usually this phantom is used to indicate the dose that received by the patient itself, the human itself. So whatever the dose received in the phantom is should be similar to that in the patient. So phantoms must have a very specific characteristic, and that involves several characteristics such as the mass density, which is 1.0 over gram centimeter cubic, which is equal to the value of water. And then other characteristic also is the effective atomic number, or Z effective, of 7.42. This is based on the AAPM report 21 in 1983, and also the mass attenuation coefficient that very similar to water in various photon energy. So water is mentioned a lot of time here because water has been proposed as a standard phantom material in many dosimetric protocols, including the AAPM and also the IAEA. So many of the phantom available is based on the properties of water. So we cannot have the fully the accurately properties of the human tissue, then but we can still have water as the reference. And other than water, there are also several other solid phantom materials that is made water equivalent. This is due to the properties of water that is liquid, and there will be some compatibility issues with some of the radiation detectors. So some solid phantoms are brought up into the market, and usually they are made of perspex, acrylics, and then the epoxy base, and then still they will have to maintain the effective atomic number, the density, and also the attenuation coefficient to the value of water. And then there are also, but however, the most available phantoms that is available in the market still cannot fully simulate the actual properties of the human soft tissue. In terms of the radiological characteristic, there will be no problem. We can still simulate the density. We can still construct material with effective atomic number similar to the water or the soft tissues, and also those mass attenuation coefficient. However, those physical properties that involve the rigidity or flexibility, elasticity, or in some extent the change of anatomical features within the human body at the different positionings of the patient. Sometimes some of the imaging procedure that require the erect position, so the feature within the human, the organs within the body is different compared to in the supine position, for example. In mammography, so it's a special imaging techniques where it involves a compression of the breast tissues. So this is performed to obtain a uniform density of the region being imaged. Because as we know, this region has a various or inhomogeneous density of tissues. So the attenuation of radiation in this region would be varied, and that would affect the quality of the image that is produced from the mammogram. And then through the compression, it will make the tissue or the region to be imaged to be uniform, so that the attenuation rate in the whole volume of the region being imaged is uniform. So with this uniform attenuation, the image is can be clearly visualized. And then what we are looking in mammogram are usually the microcalcification. So this compression would reduce the scattered radiation by uniforming the density, and also it would visualize the microcalcification even clearer to the spreading of the tissue itself. And then most common mammographic phantom available is usually made of acrylic or perspex. And as we know, these materials are uncompressible. So the feature of compressing is lacking in many of the mammographic phantoms. So it is, the function is only limited to visualize the image, but it doesn't really simulate the feature of spreading of the microcalcification, the distribution, or the change of positioning during the compression itself. And then, and then what we do is we try to construct a phantom material made of the polyvinyl alcohol. So this material is a non-toxic and it is soluble in water. And what is most important is the density itself is near to the value of water of 1.19 gram over centimeter cubic. It means so the density itself, the density of the polyvinyl alcohol is near to the water, and then we need water as a solute, and we know that the density will not go far away from 1.0. And then it is this PVAL, polyvinyl alcohol, is commonly used in a plastic making manufacturing, and also some previous studies had indicated the similarity of this PVAL or polyvinyl alcohol gel to the human soft tissue indicated by the MRI image. Okay, so the preparation of this polyvinyl alcohol is is mixed with water, and then it is heated while mixing the PVAL into the water, and then after that we cool it down to eliminate any air bubbles within the solution, and then it is filled in the container. So that container will give the shape of the gel material that we want, and then we have to put it in the freezer to be freeze at approximately 8 to 12 hours or usually overnight. And then we have to bring it out for defrosting or thawing. So this cycle is it's called the freezing and thawing. So the defrosting or thawing would give this gel material, and this gel material that we are wanted to construct as a phantom for mammography. In our previous work, we already indicate it is indicated that the mass attenuation coefficient of this polyvinyl alcohol gel is very much similar to the human soft tissue and also the breast tissue of 50-50. So 50-50 breast tissue means 50% fat and 50% muscles. Our simulation by using the XCOM and also the SRF modalities indicated very close, very good agreement of mass attenuation coefficient at low energy photons that is similar to the mammographic energy between the PVAL and also the water and the breast tissues. And then in other work also in our previous work also, we tried to construct a bolus material made from this polyvinyl alcohol gel. So this bolus material is commonly used in radiotherapy to increase the surface dose, especially when we use electrons. So this bolus is commonly in typical treatment of radiotherapy. Bolus material is made of carbohydrate based materials. So we tried to construct a bolus material made of this polyvinyl alcohol, and we found that it functioned as in a good agreement with the common bolus material used in the radiotherapy, with only 1.5% of discrepancies compared to the common bolus material. And then we tried to construct a mammographic phantom based on the available standard phantom. So we try to simulate the calcification within the phantom, and we obtain and we successfully visualize the calcification features within the phantom. However, this is our first try, so we still fail to simulate the micro calcification. It rather look like a macro calcification. Okay, so but this is our first effort into making the phantom. And then for this work, in order to have this material that is really simulate the physical properties of the human soft tissue, such as the elasticity, the rigidity, we have to test the strength of this material. So we wanted to know whether this material is strong enough to be used as a regular phantom in our dosimetry works. So what we do is we have to test for its rigidity or elasticity or the Young modulus. So what we do is we construct we fabricate this gel material, and then we put it into a cylinder container, and then we use 10% of polyvinyl alcohol, because in our previous work indicated that 10% is good enough, is strong enough for to simulate a human soft tissue. And then we construct also another two variation which use the ethanol 50% and also graphite. So ethanol is used to reduce the density. So if we use only PVAL, we would have 1.0. And then we try to simulate much lower density material. So we have to introduce ethanol to reduce the density a little bit. And also we use graphite to increase a little bit the density. So we have three samples with one near to the soft tissue or the breast tissue. One is lower than that, maybe more simulating the fat. And also we have another sample that is higher density, and maybe it can simulate the muscles. Okay, so we use this texture analyzer to obtain the Young modulus. So what we do is we do the compression and penetration test. So we want to measure at what force, at what amount of force that the gel material starts to break. So we measure the length before compression and after the compression, and the force on which the material broke. And then as a result, so first we measure the density. So as expected, the PVAL only samples have the density near to water, which is 1.05 approximately. And then the introduction of ethanol will reduce the density slightly lower than 1.0. So this is almost similar to the fats. And then the introduction of graphite into the material would increase a little bit to 1.08, which is almost simulating the muscles. So okay, this density is measured by using a gravimetric method on which the mass and also the dimension of the sample is calculated. And then as a result, the Young modulus indicated that the introduction, so this one is when we play around with the percentage of the polyvinyl alcohol. So we try to look whether the percentage of PVL would affect the Young modulus of the sample of the samples. So we prepare 4 samples between 5% to 20%. And then we found that when the percentage of polyvinyl alcohol is used, the Young modulus would increase. And also the force required to break the sample is larger. And then for the thawing process, so that means the freezing and defrosting. So if we repeat the process of thawing, so the Young modulus would increase. So that means the strength or the elasticity of this material, this polyvinyl alcohol material, would increase if we conduct more than one cycle of freezing and thawing cycle. And then for the samples of polyvinyl alcohol with ethanol and graphite, we also find out that the use of ethanol and graphite also increase the Young modulus of this gel material, and also the force required to break it. And then from the result also, it is indicated that the sample with graphite showed a tremendous increase of Young modulus when 2 freezing and thawing cycle is used. So this is maybe due to the properties of graphite that would fill any void within the matrix of the polyvinyl alcohol gel material. And then when we look at the scanning electron microscopic images, so we can see that between the samples, the polyvinyl alcohol with graphite have a very smooth structure, indicating that the graphite molecules had filled up all the void or empty spaces between the matrix of the polyvinyl alcohol. In comparison to the polyvinyl alcohol alone, so we can see that there is irregular densities. So that also indicate a lot of some void spaces between the matrix. And then after that, we try to repeat the microcalcification. This is our recent findings. So we reconstruct the phantom, and we try to simulate the microcalcification as well as the mean glandular dose. And then from the finding, it is found that the polyvinyl alcohol phantom that we construct was able to simulate the microcalcification features, passing all the diagnostic or evaluation by the radiologist. And also the mean glandular dose is also similar to the previous work on the patients. So as a conclusion, the densities of the fabricated polyvinyl gel phantom showed close resemblance to those of water and breast tissue based on the AAPM and ICRU44. And then the Young modulus for all sample increased when number of freezing and thawing cycle is increased. So if we use more than 2 freezing and thawing cycle, could be we will have a polyvinyl alcohol gel material that is more stronger. And then the result also indicated that the polyvinyl alcohol-based phantom could be used to simulate the physical and mechanical properties for the human soft tissue and specifically the mammography. But it opened up possibilities of other part of the phantom. For example, the abdomen and all those regions that have very soft tissues. So these are our references. And with that, thank you.
Thank you, Dr. Fahmi, for the presentation. We are open the floor for any question.
Assalamualaikum, Dr. Fahmi.
Waalaikumsalam.
I mean, how many cycles did you do the thawing and freezing?
At this moment, we try to because it requires
My online presentation, I will cover introduction, overview of RTP, problem background for this research, objective of the research, and next is the methodology, how we conduct the research.
Sorry, Mr. Sabri, for the interruption, but currently we at the WebEx we can see the presentation apa tu?
Okay.
Yeah. Maybe Mr. Sabri guna dua screen
Yup.
Kita orang nampak yang apa tu
Okay.
next slide.
Okay.
So kita kena matikan apa tu yang preview tu kot. Okay, sekarang okay.
Okay, alright, okay. Sorry. Okay, so I start with the overview of RTP. So as we know, we have one research reactor in Malaysia. So it's a 3 Mark 2 full type. So we are so we know the dimension of RTP is about 6.5 meter height and the diameter is about 2 meter. So this reactor is already critical since 28 June 1982. So we already operate 39 years operation. So the capacity of RTP is over 1 megawatt thermal. So the maximum of neutron flow at the center is 10 to the power 30 neutron centimeter square in 1 second. So RTP use uranium zirconium hydride, enrichment 99.9%, and we use demineralized water as a coolant and moderator. For cooling system, we use a natural convection, and to remove the heat from the core, we use a primary and secondary cooling system. And graphite acts as a reflector. To control the fission and to control the power reactor, we use a control rod, boron carbide, and RTP use 4 control rod, namely is a transient, safety, shim, and regulating. Here, I want to share, I want to demonstrate how we operate the reactor. So we need to withdraw the control rod from the core. So we need to withdraw one by one. And the maximum we can withdraw is a 381 mm, except for transient is 400 millimeter. And we need to go to critical state where at the 200. So from this point, we can increase the power linearly when we are increase the control and the power will proportionally increase. And to increase the high power like 750 kilowatt or equivalent 75%, we need to withdraw at 292 millimeter. So shut down the reactor, we need to insert the control back to the core. So at RTP, we have one console, instrumentation and control system. It's at the control room, where this instrumentation and control can control and monitor all the RTP parameters. And one of the parameter is the power. So we control the power by using the feedback control algorithm in automatic. So the feedback control algorithm, the block diagram detail can shown in the slide. So power can be divided by 2, either it's high power or low power. And then we have tuning controller parameter in the red dash line, the G1, G2, G3, and G4. And then this signal we go to the digital filter to remove the noise and go to enter to the PI controller, G3 and G4. And then we need to constrain the control rod velocity for first constraint. And the second one is after that we need to select one out of 4 control rod, because the rule of to increase the power we need to moving one control at one time. And then this control selector will send signal to the stepping motor, and each stepping motor will attach together the control rod. And when we are moving control rod, actually we are introduce reactivity initial to the reactor, and the power will be produced. And this signal will send back to the we will feedback. That's why we call it feedback control algorithm. For the problem diagram of this research, we have two. One is the transition, where FCA is struggling, or we have a longer starting time when we are trying to increase power from 10% to 75%. And it takes about 2 minutes or 120 seconds to reach 75%. And then second one is during a steady state, we have a chattering error, where chattering we measure the maximum power level and the difference between maximum and the minimum power level during the steady state. Based on these two tracking problem, so we propose FCA fuzzy power chain rate constraint in 2019. And then the result, as we can see in the slide, the red line, the solid red line is the original FCA using the constant PCRC, and the green one is the new the fuzzy PCRC. And we can see during the transition, they still cannot solve the problem for settling and rise time, and also struggle during to moving the control. We have a high fluctuation signal as shown in the green line. The green line is an experimental result where we test in RTP. And then the good thing of the fuzzy PCRC is we can eliminate and can reduce the chattering error. And as we can see, at steady state, there are small fluctuation signal and smooth signal sent to the control drive mechanism. Based on this result, we can say it's still not optimized. Then we propose a new type of controller we call is model predictive control. As we know, model predictive control is a model-based control that capable to handle the constraint in a natural way. Then for methodology, for the research, we are divided by two. First, we need to model the TP first, and then we design the control system. So for modeling, we're using the nonlinear model that we can commonly found in literature based on electronic and thermodynamic equation. And then with this input and output simulation data, we can send to the system identification in MATLAB. So this system identification can duplicate the model and transform to in the state space or transfer function. For this research, we're using a state space 10 order model. And then from system identification model, we need to combine the FCE controller, and then we need to validate the simulation model and also the experiment data. So we can see here the simulation model is close to actual model in 95% best fit, because we are to use MPC, model-based control. So we need to have a very good model if you have, in order to design a very good controller. So after we are done with the modeling, so we need to design the control system. So to design control system, we need to consider the control parameter constraint and also the safety limit constraint. For the control we need to consider the power chain rate constraint is 12.5% per second, and also the control rod velocity 2 mn per second. And for the safety limit, we only allow more than 10% overshoot at the maximum power, full power, and also we cannot increase too fast rate of power more than 33.3% per second. It is for safety analysis report in M&A. For methodology, for MPC, we have two. We propose two. One is without the PCRC component, and the second one we combine the fuzzy PCRC. So MPC, the good thing we need to include the constraint. We need to define the constraint. First, we include the constraint for input constraint is control velocity 0.4 equivalent to 2 mn per second. And then to improve the performance, we introduce the cost function. As you know, cost function is we need to have a minimize a value of cost function, as RS is a power demand, Y is output. Is RS is Y, and the performance of MPC by using cost function quadratic programming. Based on this optimizer equation will embedded to MPC, and the MPC will produce the control signal U and then send to CRDM and to try to move the control, and power will be increase, and the new power level will send back to the MPC, and then MPC will update the new control signal. This is the first approach for MPC and PCRC. And the MPC, we need to tuning the prediction horizon NP and the control horizon, because MPC is have ability to predict. So the two at the left side is the lower from NP10 to 80. We can see they have a very fluctuation, but in a stable manner, because the plant is stable, so we can control plant is stable. So, but we can see in the actuation signal, the signal to send to control drive mechanism is very worse. So this can be damage to the control drive mechanism. So we need to increase the number of prediction horizon from 90 to 200. So we can see the result is significantly improved, and with a no fluctuation signal and have a small overshoot, and we select the lowest overshoot and the smooth control signal. So NP equal 100, so equivalent to a 200-second prediction. And the control horizon for this we're using is 5, equivalent to every 1 second we'll update the new control signal. For the second one is we embedded MPC and fuzzy PCRC. So with the same fuzzy presented in the previous slide, and the new MPC and fuzzy PCRC we use the triangular membership function based on Tegaki Suguno. I'm already presented in the 2019. So based on this algorithm, we try to combine with a different controller, and we try to investigate the difference between controller type using the same fuzzy PCRC. And the result we can see here, with the original one, the FCA fuzzy PCRC is the red dash line, and with the MPC, non-PCRC, and the fuzzy PCRC can improve the transient performance a little bit with small settling and rest time, but have a small overshoot. Okay, and for the actuation signal, using PCRC, we can see that the red dash line, fuzzy FCA fuzzy PCRC and MPC fuzzy PCRC have a small fluctuation. They have to reduce the signal due to the rate of power tend to close to 12.5%. But MPC for non-PCRC is not considered the second constraint, just only control velocity only. So just maintain at maximum speed. And another one is MPC is struggle to reduce the signal from maximum velocity 0.4 to stop the control to 0. And then this could happen due to the mismatch model between city identification model and also the actual. You can see in the right top, the purple one is the city identification model we're using for MPC, and the green one solid line is the actual model. So based on this, you can see when we are stop the control movement from the blue signal here, then the power will reduce from 80 to 60%, and there's some delay. And also this, because this strong non-linear, the MPC struggle to control. So because we are currently use a linear MPC, but this result still can be accepted. And then based on these two figure, we tabulate in this table. We can see the MPC can have a small setting time improvement like 2%, rise time small, quite a similar number with certain time, and they have a little bit percent overshoot, but still below than 10%. And the chattering error during the transition higher than the FCA fuzzy PCRC due to the percent overshoot. But the good thing is during the steady state, the MPC have a better result for chattering error during steady state. And the offset MPC, second problem for MPC due to the mismatch model, we have offset error is 0.01%. And then between FCA, fuzzy, and FPC, they have a similar workload, and but better for the energy release. For mean they are optimize the power in the reactor. So the energy release we are calculated based on the area under the graph. Okay. As in the previous in the early slide, I already mentioned the shattering error less than 2%, and here is the result for simulation. So previous result we are validate with the experimental. So FCA fuzzy get 1.25%, and you can see the difference between the experiment and the simulation, because the simulation is not include the noise, and the experiment we have a noise and also uncertainty. So it's about 98% different. But the MPC fuzzy, due to the time constraint and the complex procedure, we need to have permission from the safety committee and also regulatory body, so we can conduct the experiment. So it's not available, but we try to estimate by using the same error. It's 98%. We can get this kind of value as 0.1234. This value, and then this value still need to validate 0.2345. Okay. Here can you see the MPC without PCR and using the PCR, the result is still the same, because we are using the only 2 mm control speed. Next, we try to increase the control rod from 2 mm to 3, and we use a high reactivity insertion rate instead of using 4 control rod, using the single regulating rod. And this experiment in order to test the robust the MPC. So MPC non-PCRs is more than the parameter, the exceed 12.5%. But MPC fuzzy, they are still in boundary less than 12%. Even they have using a higher reactivity rate and the control speed at the maximum 3 mm per second. And the significant improvement is when we use a high control rod velocity for the wide range power from 10 to 275, there are small fluctuation signal. We can see in the dash a black line compared with the without PCRC. Okay, for the future work, we try to solve the problem with we try to combine the two benefit of controller. For MPC is better for transient, and FCA and fuzzy is better during steady state. We can use a switching model, and this research will conduct in the next. And for conclusion, we can say that MPC fuzzy PCRC can provide a greater safety, and it's very useful for type of nuclear reactor that require type multiple constraint, because they are not only solely in one parameter constraint to get the power. And another one is the MPC and also fuzzy can we can say is can mutual understanding and can collaborate each other due to different function assigned, and we can say is other alternative solution to optimize the trigger power control format. So due to that, I thanks to the Dr. Nur Adila is the team leader for this project, and also for management agency, and mostly for the support. It's a reference for this paper, and that's all I say. Thank you.
Thank you very much, Mr. Sabri, for really, I think, good research in order to optimize our one and only research reactor in Malaysia. So I open the session with Q&A if anyone want to ask Mr. Sabri about his work. Okay, but in the meantime, I would like to acknowledge and thank all the research officers there in Malaysia Nuclear Agency. Like Mr. Sabri said, that research reactor almost 40 years old, but they still optimize and still maintaining the research reactor so that we can still use it for various research and even for analysis and for the industries, for the academician to use it. So I would like to thank that to all the research officer there. Okay. Any question for Mr. Sabri? Actually, this is not my area, so I'm not sure whether I can to ask any question out of it.
Okay, thank you, Dr. Shaya. As you know, we are already 40 years operation.
Yeah.
So we can estimate maybe our plant RTP can operate until 50 or 60. It depends on the fuel available. If we cannot optimize the way we operate, we cannot extend the lifetime of the operation because due to that, because we need to improve the control performance for this RTP because the RTP we have only one. We cannot we don't know after we are 10 to 50 years later we don't have any nuclear reactor. Maybe depend on the policy government. So we try to optimize. If you have some research, we can go to RTP. We are open.
Yes, yeah. I think this conference is good for the student or maybe future student if they want to do research at Malaysia Nuclear Agency. I think all the research officer there welcome for all student, academician or researchers to do research there. Okay, so I think if there is no other question, I thank you, Mr. Sabri, for the presentation. I think we shall proceed for the next presenter. Okay, but
thank you.
Okay, thank you. Okay, from my from the tentative, the next presenter is on the integrity of reference source used for those calibration tests that will be presented by Madam Noriza Muhammad Isa from Malaysia Nuclear Agency, but seems that she is not joining yet at this moment. So I think I will replace her session with my presentation. Okay, so let me share my slide first. Okay, so my presentation today is entitled New Exposure Room Shielding Incorporated with Ferroboron Concrete for Neutron Radiography Imaging. We call it as NURI facility at Triga Puspati Research Reactor. So like I said before, Malaysia Nuclear Agency always welcome any students or any researcher to do work there. So I'm one of the students do project at Triga Puspati. So these are the members that I collaborate with during this project. Okay, this is my presentation outline. So I will briefly give the introduction about our facility, and then I will go to the methodology for this work, and I will explain a little bit briefly about the result and discussion. I will not go into so detail in the technical term. Okay, and lastly, I will go to for the conclusion. So, but before I start with the project, I just want to give some information about our newly established research group. We call it as Advanced Nuclear Engineering Research Group. So we are based in UTM. So prior to this research group establishment, just for your information, UTM has offered Bachelor of Engineering Nuclear, okay, since 2012. Okay, so since that we have enrolled around 250 students, okay, up until today. So in this research, okay, prior after that, after we has the curriculum to stabilize all the instrumentation is there, we now focus on the postgraduate student and more researchers, more research. So at this moment, we have 8 members for research group, okay, from various background. So we have 8 research area that we want to focus, including NDT, nuclear instrumentation, nuclear NPP siting, and many more. So this research group established in December last year. Okay, so this research group focus on the nuclear technology, techniques, and application. So we are welcome for any collaboration after this. So we can you can contact us, or you can straight away email me, okay, for any collaboration. Okay. So now I will start with my work. So for the introduction, okay, neutron radiography has started way back in 1935. I think actually 3 years after the discovery of neutron itself by the English researcher James Chadwick. Okay, this neutron actually is a particle that bind together in an atom, okay, with proton. Okay, neutron has naturally charge, so it has no charge. So a neutron give a special, unique characteristic compared to X-ray or gamma ray. Okay, so neutron actually didn't interact with the electron, right? Rather, like X-ray and gamma, they interact with electron, but neutron interact straight to the atom, to the nucleus of the atom itself. Okay. So that one is the introduction for the neutron. Okay, currently there are about 50 neutron radiography facilities around the world. Okay, one of it is in Malaysia at RTP. So like Mr. Sabri said, in Malaysia we have one and only research reactor. We call it S3 Mark II Puspati Research Reactor, which located at Malaysia Nuclear Agency. So the age of that reactor is almost 40 years old, but we can still use it. So we should use it, and we should optimize it and fully utilize, okay, before late lah, before we cannot do anything with the reactor because of the fuel burn up and so on. So in Malaysia, we started our neutron radiography facility journey, I so called, since 1983. Okay, about 1 year after the commission of the RTP itself. Okay, so at the early age, I can do a pointer. So we started, they started, the research officer at Malaysian Nuclear Agency at that time started with, they call it as NURI 1, built from modular concrete blocks, small modular concrete blocks. Okay, they install it in radial beam port 1. Okay, from this system, they collect all the data, all the information, so that they can build a permanent neutron radiography facility for RTP. So around 2 years of data collection and experiment. In 1985, they relocate the neutron radiography facility to beam port number 3. Okay, during this time they already have the permanent exposure room. Okay, all this design are based on the data from this first system. So this system known as NUR2. So the NUR2 is, I think it is utilized by many academicians, by many industries, okay, to do research, to do studies on various of field, okay, in agriculture, in heritage sample, in turbine and industry, many application, okay, since 1985 and up until 2014. Okay, due to some limitation for NUR2, okay, for the beam quality, high gamma radiation, they also have a problem in terms of its shielding bunker itself. They have a streaming problem. So research officer during that time agree to upgrade the system totally, okay, revamp all the system. So they firstly remove the old collimator so that they have a space to install a new collimator. Okay, from since 2014 and up until before we open the new system, the NR application was used temporarily at small angle neutron scattering sense at beam port number 4. Okay, so after 2014, series of research and design had been done, okay, in order to upgrade the overall system and instrumentation. Okay, so but I will not go to the imaging system, to the collimator. I will only focus on the exposure room shielding. Okay, so in 2018 we install the new shielding and new system. Okay, so for this exposure room shielding, we use new material. We call it we use new material, which is the ferroboron. Okay, why we use ferroboron is because as you know, neutron, like Dr. Arif just presented before this session, when we dealing with neutron, we have to use special material. We cannot use only one material. So we have to thermalize the fast neutron, and then we have to absorb the thermal neutron, and that thermal neutron will eventually produce secondary gamma. So with that, we try to introduce new ferroboron to compensate all the radiation from neutron and gamma. Okay, this new system, we call it as NURI. Okay, the new system, we call it as NURI. Okay, so based on previous presentation, if you join the pre-conference workshop, Dr. Rawi has already shown the capability of the new system. Okay, now we can offer the tomography imaging. So basically now the system now is on digital imaging. Okay, the previous one in NUR2, we are limited for only conventional film radiography. So the new system, we can offer digital, so the result for our imaging is spontaneous and fast to get the result compared to the conventional film. Okay, so I think like Dr. Rawi said, they are welcome for any academician, researchers, industry to use the system now. Okay, for various of application. Okay, this is the picture for the permanent neutron radiography facility NUR2 back in 1985. Okay, I found this picture in 1987 paper from Ramli, status of neutron radiography in Malaysia during that time. Okay, for this for my presentation today, I will focus on the Monte Carlo simulation code MCPX. So the data here is all simulated data. Okay, so this simulation is to study the overall performance of the new exposure room shielding. Okay, we tested several cases, so I will show it later. What is the case that we had simulated? So in MCMP, we have to create the input file. So it consists of the radiation source, geometry, okay, and the output that we want to simulate. So for the radiation source, we assume that we operate the reactor at 1 megawatt power, okay. But the actual situation, we only operate at 750 kilowatt. So we maximize, we simulate the maximum reactor power that RTP can go. Okay, so the radiation source is based on previous study by Mr. Hairi. Okay, and the data set is from ICRP 20-1971. Okay, that one is for the radiation source. So for the geometry, okay, the dimension of the exposure room shielding and the material used in the simulation are based on the actual design. We try to simulate as close as possible to the actual situation in RTP. Okay, for this presentation, I will show 4 different cases in our simulation. Okay, for the output, we want to measure and we want to map the dose rate around the new exposure room shielding by using the MCMPX mesh tally. And then that data from the mesh tally, we convert it by the flux to dose conversion factor. And then we calculate the total dose rate from gamma and neutron radiation. Okay, and then the data will plot it in contour plot using Excel. Okay, and you will see the plot after this. So these are the geometry for the simulation. So this is the top view. As you can see, this is the collimator of the neutron radiography facility. Okay, this is the new design. Okay, and then we have the beam shutter. Okay, so the gray one is the we call it as the ordinary concrete. Okay, but in this case we use grade 40 concrete. Okay, and the red area here is ferroboron concrete. Okay, as you can see, we didn't build this exposure room totally with ferroboron. Okay, firstly due to cost, okay, and limitation of the raw material of ferroboron because it is quite expensive. So we only optimize it at the direct beam. Okay, I will show it later why we put the ferroboron here. Okay, not other parts of the shielding. So these are the simulated case that been simulated. So the first case is without any shielding. We just want to know what is the behavior, what is the characteristic of the radiation without the shielding. Okay, we want to know the beam line, the beam line of the radiation. Okay, the second one is the exposure room shielding with ordinary concrete only without the ferroboron. And the third one, exposure room shielding with ordinary concrete and ferroboron. And lastly, the exposure room shielding with ordinary concrete and ferroboron with beam shutter closed. Okay, so the beam shutter is in this simulation consists of 30% operated polyethylene with thickness of 10 centimeter, lead with thickness of 15 centimeter, and lastly we have the barite colomanite concrete with thickness of 25 centimeter. So also the shutter composition and dimension is based on the actual one that we fabricate. So moving on to the result and discussion. So this one is for the first case. So these are the contour plot that I plot. Okay. So as you can see, without any shielding, so these are the beam opening lah, like right here. We can measure the highest radiation dose. Okay. At the beam opening is around 0.13 sievert per hour, which is very high. So that beam line will straight away go to the reactor hall room lah. Okay, this one is just to show the strength of the radiation. Okay, the second case, we put the exposure room shielding, but it is from ordinary concrete only, which is the grade 40 concrete. Okay, as you can see, they managed to contain the radiation inside the exposure room, but the radiation dose rate at the back of the shielding wall, okay, at the straight beam, okay, the radiation is around 3,000. Around 3,000 for around 3.4 millisievert per hour. Sorry, 3.4 millisievert per hour, which is very high. Okay, this one is without any special material lah. It is a normal concrete. Okay, that is the reading that we got from the simulation. Okay, but the other part of the exposure room, the radiation is around 1 microsievert to 10 microsievert. Okay, I think the other part is quite acceptable. Okay, except for the straight beam line here at the back of the exposure room shielding. Okay, so with that, we have to introduce some unique or special material in order to contain that high radiation. So we introduced the ferroboron concrete. Okay, so as you can see, we managed to reduce the radiation by factor of 1. Okay, which is around 1,100% of reduction. Okay, as compared without any ferroboron concrete. So now the radiation is around 300 microsievert. Okay, it is considerably high. Okay, as compared to the safety standard. Okay, then I will explain it later. We have to further studies in designing a new beam stopper. Okay, to tackle this problem. So the next case, we have same ordinary concrete with ferroboron here, but in this case, we close the beam shutter. Okay, so sometimes when we do the Newton radiography, we have to change the sample. Okay, so we want to know whether it is safe if we can maintaining the reactor power at the operating level, which is the 750 kilowatt, and we just close the beam shutter and we can play around with the sample. Okay, based on this simulation, we can see that the radiation dose rate at the back of the beam shutter is around 400 microsievert per hour, which is high. So we suggest to all the users, okay, to at least lower the reactor power or shut down the reactor first, okay, when we want to enter inside the exposure room shielding, okay, because when we operate the reactor at 750, the radiation or the radiation coming out from the reactor, the beam is high, and it is not safe to workers, okay. But when the beam shutter is closed, or the radiation dose rate around the facility is around 1 microsievert. Okay. So for the conclusion from this simple simulation, I can say that this simulation has simulate the total radiation dose rate mapping for the new exposure room shielding for NURI. So for RTP has been simulated in the study using Monte Carlo simulation code of MCMPX. So there are several outcomes. So the first one, we can say that the ferroboron concrete can significantly reduce the radiation dose rate by 1,150%, okay, compared to the ordinary concrete. So the ferroboron concrete mold in the spherical shape to optimize the usage of ferroboron, because we have the limited ferroboron. Okay, so we can say that the proper procedure and precautions still need to be taken for all the facility users. Okay, especially when the reactor power at 750 kilowatt at the operating level. Okay. So, and for the studies, we have to consider to put beam stopper at the direct beam. Currently, I think we install temporary beam stopper. Okay. So lastly, I would like to acknowledge the simulation software used in this paper was performed and used using Malaysian Nuclear Agency license. Okay. And the author also would like to acknowledge all the contributors in completing this paper. Okay. I think that's all for my presentation. I would like to open for any comments or question. Thank you. So let's see. Okay. Is there any question? So I see Madam Noriza is here now. So Madam Noriza, can you maybe you can present after Miss Nasuha? Is it okay?
If Madam Noriza want to present first, she can do it. Then I can wait.
Sorry?
If Madam Noriza want to present first, yes, she can do it. I can wait for the next.
Okay. So Madam Noriza, you will present. But in the meantime, if there is a question for my presentation, you can put it in the chat or straight away ask me. Okay, once again, I would like to thank Malaysian Nuclear Agency for giving me chance to, collaborate with them. Okay, I gain many experience when do that work. Okay, during my PhD. So I would like to thank here I can see Dr. Julie, Dr. Farida. Okay, before this I can see Encik Hairi. Okay, all the research officer there. Even Madam Noriza helped me use the lab for TLD. Okay, I would like to thank all of them. Okay, if there is no question, I think that's all for my presentation. We will proceed to the next one. Madam Nuriza, are you ready for the presentation? Or we can proceed with Miss Nasuha first. Yeah. So maybe we can give Madam Nuriza time. So okay, Madam Nuriza is here. Okay, so we will move to the next presentation that will be presented by Madam Nuriza Muhammad Isa from National Agency. So her title will be on the integrity of reference source used for dose calibration test. So without further ado, I would like to pass the session to Madam Nuriza. Puan Nuriza, saya rasa apa tu kita dengar echoing.
I think better you give to other presenter. I got problem.
Okay, sure. So I think we will go for Miss Nasuha first, then we will continue back with Madam Noriza. Is that okay, Miss Nasuha? Okay, thank you. So before we proceed, to Malaysian Nuclear Society YouTube and you can watch there. Okay. Okay, so Ms. Naswa, are you ready to present your paper? And also I would like to thank all the participants who stay with us up until this afternoon. Okay.
Dr. Shai, can I start first before Miss Nasuha now? So you want waiting for Miss Nasuha?
Yeah. Okay, Ms. Naswa have got problem with microphone. I think we can proceed with Madam Noriza first. So for Ms. Naswa, I think you can log out from the WebEx and you can join again. So maybe sometimes the WebEx got problem. Okay, so you can stop sharing and we will allow Madam Noriza to present her paper first. So Ms. Naswa can leave the WebEx and join it again. I think it will help, inshallah. Okay, so sorry for the technical.
So for that, I try to deliver the integrity of reference source used for those calibrator. Okay, this is the content of our presentation. We try to go the introduction, methods, data analysis, result and discussion, and lastly conclusion. Okay, as an introduction, you know, the dose calibrator is one of a detector. This is the gas ion chamber. This is the gas field detector. Because gas field detector, we can category three category of the gas field detector, which is the ion chamber, proportional counter, and GM. That's mean the Gigi-Miller counter. But for dose calibrator, we are focused on gas field ionizing chamber with highly pressure to increase detector efficiency. The gas in the ion chamber of those calibrator is always, for example, argon, xenon, and so on. Okay, used to measure the activity of radionuclide. Those calibrator is always used in nuclear medicine for diagnosis purposes. The range of the activity we can measure using the dose calibrator is around 1 microcurie to 20 curie. This is the range of the dose calibrator in nuclear medicine. Okay, the dose calibrator used in nuclear medicine to measure the amount of the radioactivity of radionuclide before injection into the patient. Okay. Okay, the dose calibrator, before you want to use the dose calibrator, or you must make sure the dose calibrator should be calibrated. So in Malaysia, we have the secondary dose calibrator we call the Fidelis radionuclide calibrator. The dose calibrator will use to as a reference, okay, for the user dose calibrator in hospital in Malaysia. So in the Fidelis radionuclide calibrator, we have the Fidelis software. We also have reference standard radionuclide, and we also the deeper and also the liner for the Fidelis radionuclide calibrator. And the same thing is similar for the users dose calibrator. We have, for example, we have using what we call the tapping text model. For example, this is we use the CRC 15R software. And for the user, we need to do the daily test for their dose calibrator. And the same thing with the Fidelis radionuclide dose calibrator system, we have also the dipper and the liner. So the dipper is used to put the radionuclide in the syringe or in vial, okay, before we inject to the patient. Okay, routine work. Monthly check source response is always do by the technicals in the nuclear medicine department. So we need to know the deviation of the accuracy for the check source is around plus minus 5% deviation. And also the linearity of the reference source for the daily test is around 5% deviation. That means we must to measure first using your dose calibrator, and also you compare with the calculated dose activity. Okay, so from there you make the deviation, so must be have the tolerance limit plus minus 5%. So almost the environment control for dose calibrator, we have a 24 hours air condition to make sure the temperature is ideally 23 of centigrade. Okay, this is one of the condition for the dose calibrator. Okay, in nuclear medicines room. And then this is the flow chart, how the calibration test process. Okay, in nuclear Malaysia, first thing we have received and register the dose calibrator from the hospital. And then after that, we make the physical inspection of our dose calibrator, and then we do the calibration test. Either some of the tests including contamination test, accuracy test, consistency test, linearity test, geometry test. But for today, we are more focused to accuracy test. Okay. And then after that, we have data analysis and produce report, and also certification of the dose calibrator. And then we return back to the user. Okay, calibration tester or equipment required for the calibration of dose calibrator test. Okay, for dose calibrator secondary, we need to use the Fidelis, and we use the dipper and also the each well liner. And the same time, we use the reference standard radionuclide. And then we need also the tissue closed for cleaning, forceps, surgeon's glove, survey meter to make sure there are no contamination during you are doing the calibration test. Okay, and for this step, we need 4 radionuclide reference source, which are cobalt 57, cobalt 60, cesium 137, and barium 133. And also for the decay or shell method, we also to do the Kelly check tool for linearity test. At the same time, we need to use the daily radionuclide used by the hospital, for example, technetium 99M, fluorine 18, or the 131 to test the linearity and the accuracy using the calibration system. And then we need to do special lab pot, to put back the radionuclide after we have finished the test. Okay. And then this is also how we need to do for the dose calibrator calibration test. We do some parameter. For example, we need to do the stability test, contamination test, accuracy test, consistency test, linearity test, and also the geometry test. Okay, first thing you must to make sure the equipment is stable, and then after that we do the contamination, and then if the contamination is passed, then we go to the accuracy and precision test. After this is okay, we go to the consistency test, and then go to the linearity test, and lastly we go to geometry test. Geometry test we can divide 2 tests, which is the vertical test and horizontal test. Okay. So as you know, okay, the dose calibrator in Malaysia we have a lot. It's around more than 20 nuclear medicine center. 5 nuclear medicine center in Pulau Pinang, Pahang 2. Okay, Nuclear Medicine Center, Kuala Lumpur 9, Negeri Sembilan 1, Melaka 1, Selangor 4, Putrajaya 2, and Johor 3. And also we have also the Sarawak and Sabah ones. Okay, and if you look at the brand in Malaysia, mostly we are using the Biodec medical system. This is around 60%. Okay, for this carburetor used in Malaysia, and the other we are also we are using the Capintec. Okay, and the others brand PTW, Venstra, and Isomed. Okay. And then if you look at the Nuclear Medicine Center, this is the hospital that I know you are familiar for the name of the hospital, Hospital Kuala Lumpur, Hospital Putrajaya, Hospital Pulau Pinang, Hospital University Science Malaysia, Prince Court, this is a private hospital. And then KPJ is also private, Mount Mariam private, Penang Adventist, and Island Hospital. And we also cover the government hospital. Okay. And then we now go to the integrity of the radionuclide, which means the integrity. Integrity, that means we are focused directly to the some word we call the recommended working life. Okay, what the definition of the recommended working life, or RWL, is a finished lifespan of radionuclide recommended by manufacturer. Okay. So some other definition we can defines the finite life of the source, after which the source is no longer considered to provide adequate containments of the radioactive source material, or you can define the RWL as the useful life of the source. That means the radionuclide source, after which is no longer delivering a dose adequate for the application. Or some other definition, a set period of time after which the source must be inspected and assessed to determine if it can be further remain in service or not. For example, you can look at the what we call the RWL, stated by the manufacturer. For example, we have the cobalt 60, for those carburetor. We have the cesium-137, barium-133, and also cobalt 57. The range of the RWL is around 5 to 10 CS. Okay, this is the example of the RWL recommended by the manufacturer. So, but the definition given by the IAEA safety guide, that's mean on safety of radiation generator and C radioactive source address, RWR, as follows. Some manufacturers also specify a recommended working life of source, which is the period of time over which the source is expected to maintain its integrity. Okay, in the specifying the recommended working life account is taken of the nature of the radioactive material, its half-life, and the encapsulation of the source. And a source that has exceeded its recommended working life should be inspected by the manufacturer or other appropriate body to ensure that the integrity of the source has been maintained. The regulatory body may permit sources that have exceeded their recommended working life, or RWL, to continue in service subject to confirmation of continuing integrity. This is the very broad definition of the RWL. That means what is the meaning of the integrity of the radionuclide stated by the IAEA. So based on the definition, so I was doing the investigation about the RWL for our radionuclide source for those carburetor tests. For that, we try to do some procedure. So this is the method I was doing before. First thing, before we use those carburetor, we are doing the daily test using the Fidelis system. And then the second method, we try to monitor the output. That's mean in PA, that's the currents of the reference radionuclide using Fidelis system monthly basis. Every month, we try to monitor, the reference radionuclide in terms of the current output in PA unit. And at the same time, we also monitor the activity of radionuclides, using the same dose carburetor. That's mean we are using the Fidelis dose carburetor as a secondary, And then after that, we are try to calculate what is the current of the radionuclide, and then we compare with measured PA or picoampere. So we have a two value. First, we measure by using the Fidelis. So we have the measured PA, and the second one we are try to calculate what is the value of PA by using a formula. So this is one of the recommended work life that is using in our lab as a reference source for dose calibrator. So this is the cobalt 57. Okay, we are using the 4 radionuclide for dose calibrator test. Cobalt 57, this is their activities 10.77 millicurie at 1 of June 2021. This is a quite new radionuclide. And the energy is 1 to 2 keV. This is the physical half-life, and this is the recommended working life stated by the manufacturer. The same thing for the cobalt 60, cesium-137, and also for barium-133, respectively. They have the WRF. Okay, for cobalt, cesium, and barium-133, RWS is 5 years. Okay. So now this is example of the certificate where from the manufacturer, where the manufacturer stated what is the RWL. That means if you look at the certificate, the manufacturer stated here, this source has a recommended working life of 18 months for cobalt 57. So I extract all the information regarding with the recommended working life from the certificate. So we try to use and we try to look at what happened. What is the happen if the RWF is more or less to the accuracy of the radionuclide. Okay. So data analysis. Okay. So from that, before we are try to go further investigation, we try to do the daily test first. First, we are try to check the system data check, make sure the result must be passed. And then the second daily test, we do the electrometer check, the result should be passed also. And we need to test the amplifier offset test. So we got 15.439 millivolt. So the tolerance limit for the amplifier offset test is around 7 to 25 millivolt. It's out of the range. That's mean there's some problem for our dose calibrator. And then the fourth step, we try to measure the background test for dose calibrator. This is the result 0.1 to 1, and the tolerance limit is -1 to 5 picoampere. And then we try to measure the high voltage for our dose calibrator. The result is 1454. So the tolerance plus minus 50 with the average 1450 volt. And lastly, we measure the stability of the radio dose calibrator. So the stability should be plus minus 10%. But for our dose calibrator, we have the stability is around 0.001%. That means the daily test for our dose calibrator is pass all the parameters. Okay. So this is the what we do for the currents or electrometer calculation and measure. We are apply this formula. That means AC equal AM. We time the exponential. We time also with 0.693. This is quite familiar of this number. Okay. And we time to D. We divide by PAI. This is the AC. That means the picoampere calculated. You can calculate using this formula. And AM, we measure, okay, using the Fidelis dose calibrator. And then D elapsed. That means what is the duration between the initial calculated with the with the nowadays calculated in terms of the electrometer reading. So we know what is the day ellipse. Okay. And then PAI is the initial value of PA when you started measure, okay, the radionuclide. So deviation between AC, AM, you can get what is the numbers. So we need the number to ensure our dose calibrator is okay or not. Okay. So now this is the result of the discussion. Okay, we try to monitor first for our barium-133 in terms of the picoampere or electrometer reading. So the test we call the consistency check of the barium in terms of the picoampere or electrometer reading. So this is what we look at here. The percentage deviation of our barium-133 is around -2 to 1.5. This is quite small, okay? The range percentage deviation is quite small. If more than 5, that means this is very be careful. So you need to do something for your radionuclide. Okay, if you look at the cesium-137, this is our radionuclide. It's quite old, 2010, but the barium-133 is quite new, 2013. Okay, this is quite old. If you look at the cesium-137, the picoampere in terms of positive C check, so you look at the percentage deviation between measured and calculated of PA. Okay, we look at the deviation is around -2 to 1. So that means it's also quite low, the percentage deviation for the cesium-137. Okay. We try to look at the third radionuclide. Okay. The third radionuclide is cobalt-16. Cobalt-16 is quite new, so 2018. Okay, compared to the barium-133. So if you look at the same, okay, percentage deviation of the cobalt-60 in terms of calculated and also measured deviation, you time with 100, you can get this value, and then you plot it against the day ellipse, so you can get this distribution. So again, if you look at the percentage deviation is around, it's quite small compared to the barium and cesium-137. It's around -0.6 and 0.6. So this is quite smallest compared to the barium and cesium, okay, before. Okay, then the last reference source for those calibrator is a cobalt-57. If you look at the cobalt-57 and cobalt-60 is not give the big difference in terms of the year where we are obtained from the manufacturer. So we try to monitor what is the PA value in terms of consistency check. So we try to get the deviation percentage, okay, between measured and calculated of the PA, and then we got this is quite divergent of the percentage, deviation percentage. It's around -30 and +40%. That means this is some problem because we can look at actually at after 1,000 something day. That means around 2017, 2018, we have got problem for our source here. Okay, so we need to ready and try to check what happened to our cobalt-57. Either they have some problem in the leak test, or maybe they have some contamination in our lead pot, or maybe some other crack of our what we call the housing of the cobalt-57 and so on. Okay, so for this result, we can plan what we must to do for the cobalt-57. Either we want to buy the new one, or we want to try to double check what happened to our cobalt-57, because if you look, the deviation percentage is quite diverge. Okay, it's quite large, the variation between the initial value. Okay. Okay, if you look more further investigation, okay, in terms of the deviation measured and calculated also, we can look the graph here. The graph here is almost for cobalt-57, the day between, okay, 0 to 1,000 something, 1,200 day ellipse. Okay, the variation is quite small, but after 1,300, the deviation is quite more. Okay, either a positive part or negative part. From that, we know what we know some problem with our cobalt-57 in terms of the integrity of cobalt-57. And then the same time, if you use the same cobalt-57 for the calibration test in terms to determine the accuracy of the cobalt-57, so we look at the result, okay, between the reference. The reference, if you look at, is quite fluctuate, not consistent. And you look at the standard deviation, is quite more, 55.67. So the uncertainty of type A is quite bigger. Okay. And also for the test, okay, for the test is quite fluctuate also. This is using the end user dose calibrator. This is using the reference dose calibrator. That means we are using the Fidelis. based of this result, we can look at what happened to the calibration factor. That means the CF. CF for the dose calibrator by using the cobalt 57 is 0.765. This is we can call is quite worse for the result of calibration factor. For tolerance limit, MOH nation, MOH, we try to get the calibration factor for the radionuclide either for cobalt 57, cobalt 60, barium 133 or cesium 137 is around 0.95 and 1.05. That means plus minus 5% or 10%. Okay, the calibration factor. But because we are used the problem in the integrity of the cobalt 57, so we cannot get the calibration factor around this limit. So be careful when you want to use the reference source. You must make sure the source is quite good integrity. Okay, compare to the others. Okay. So as conclusion, okay, accuracy of the calibration test depends on the recommended working life of radionuclide. And the second conclusion, consistency of radionuclide in terms of electrometer reading, in terms of pH should be regularly monitored. And measured and calculated activity should be monitored regularly. That means in monthly basis, user can use directly the reference source to check the performance of those calibrator without knowing the accuracy of their radionuclide. That means the integrity of their radionuclide, especially for in terms of recommended working life. Okay, so you must double check first before you use the radionuclide for your measurement. Okay, for this, I want to acknowledgement to the medical physics staff and nuclear Malaysia who are carried out and involved in the calibration test for those calibrator, and also appreciation to nuclear Malaysia for giving us the budget to obtain some equipment and radioactive source to perform the calibration test. And thank also to Ministry of Health, okay, giving H license to our team for doing calibration test of those calibrator in all nuclear medicine center in Malaysia. Okay, and then this is our references, and thank you for your attention.
Okay. Actually, we are up to a bit time constraint here, but maybe if Puan Noriza can answer short and sweet for one question from Dr. Amira. So the tighter integrity of reference source can be a tremendous issue. So can you share the current status of the reference source available in the world?
Current, can you repeat the question?
Okay. Or maybe Madam can stop sharing, and the question is in the chat. So the question is, the tighter integrity of reference source can be a tremendous issue. Can you share the current status of the references sources available in the world?
Okay, mostly in the world, if you look at IEA and other primary standard, they are also use the same name of the radionuclide. For example, we can use the cobalt 57, barium 133, and we also use the cesium 137, and also we can use the what we call the cobalt 60. Why we need all these radionuclide? Because the range of the energy of radionuclide used in nuclear medicine range for diagnosis purposes. So that's why international also recommended this radionuclide can be used to do the dose calibrator test for the dose calibrator in the world. So I try and I give effort to get this radionuclide, but you must make sure all the radionuclide must be traceable to the primary lab. For your knowledge, our radionuclide source is traceable to NPL. This is the secondary lab dose calibrator in the world. Okay.
Okay. Thank you, Madam Noriza. I hope that will answer Dr. Amira question. So yes, thank you again. So due to the time, we cannot open another question. So we will proceed our last presentation for morning session. Okay, with titled Investigation on Physical Properties of Various Grades of Trigas Fabrication Ordinary High Density Concrete by Ms. Nasuha Ahmad from UKM. So please, Ms. Nasuha, the session is yours.
Hello, can anyone hear me?
Yes, yes. Okay.
I'm so sorry about just now. Okay, I will start my presentation.
It's okay.
Okay, do you?
Okay.
Okay.
All right.
Okay, my presentation on investigation on physical property of various grade of trigger fabrication, ordinary and high density concrete. So actually I'm doing, on my research, I'm doing two types of concrete, which is ordinary high density and barite high density concrete. But for this iNUSTEC, I will just present an ordinary high density concrete. It's just a part of my research. So, as we all know that concrete is the largest and irreplaceable section commonly used in nuclear power plant for the structural application and radiological safety. It provides significant part of safety and containment system and also used as biological shielding to protect personal public. My research actually I adapted from Zagar and Rebnik 2002. They're using the composition of ordinary concrete from Triga alluviona and I modification their research by upgraded it into a various grade of concrete, but I'm using the same material as them using. So the problem statement is degradation of concrete in Triga due to the neutron irradiation could be occur after 37 years operation. I'm doing this research start about 3 years ago, so it's 37. And it's only focused on dose absorption rate of concrete wall and analysis of crystal structure change in morphology of concrete structure caused by neutron are not clearly visible and observed. So degradation of concrete leads to leaking of fission product and significant radiation exposure to worker and public. So because it is possible for us to collect the real concrete sample from the trigger, thus fabrication of variation mixture of concrete are essential to stimulate the neutron irradiation on concrete. So that's why I fabricate the trigger concrete by using the previous research so that I can see their morphology and crystal structure. So objective for this presentation just to measure the physical properties of fabrication concrete and to investigate the morphology and structure of concrete before the irradiation process. So for the first metallurgy, of course, I have to make the calculation how many material that I want to use to make the different grade of concrete. So we using standard, but I forgot to put the name of standard here. So as you can see, the amount of water doesn't change at all. And we made for concrete 3 in this size, 150 cubic, and the bigger one, 100 millimeter and 740 millimeter. For the aggregate, I'm using for the coarse aggregate, I'm using limestone, and for the fine aggregate, I'm using silica sand. So it's supposed to be for the cement, the higher the grade, the more the volume of the cement also increase, same to the other materials. Okay, then this is the process I'm doing concrete. I'm doing concrete by myself. I start by mixing all the material in concrete mixer and I mix them for 20 to 30 minutes to make sure they all mix together, put in the mold and put them in the mold on the vibration machine to make the concrete dense and compact. After that, I dry the concrete for 24 hours. But for barite concrete, I dry it for 48 hours and then undergo the curing process by curing in the tap water for 7 days and room temperature for 21 days. Curing must be done at least for 28 days because it's really necessary to obtain the compression stress up to 99%. And then after that, I'm doing the compression and density test, and then I cut the concrete into the size that I want, and my concrete is ready for the experiment. So, physical properties after curing. After curing for 28 days, I calculate my density. I forgot to put minus and plus on the back of this one, and the compression strength. But as you can see, it's supposed to be that grade 50, grade 35 has a lower compression strength compared to 45. But in my case, I don't know why, but compressive stress of grade 35 is higher than 45, and it might be with something that I'm gonna discuss after this. So for actually I'm doing a lot of type of examination, but for this research iNUSTEC, I just present my petrography examination. So this is a result and discussion. Okay, for petrography examination, I must prepare the sample until they become like this. With the cross section, I think the thickness is just 0.03 millimeter. I forgot, and I'm using a polarized microscope. So first of all, as you can see from my ordinary concrete grade 50, you can see I'm using for the all texture, I'm using the plane polarized view, plane polarized, and this is the first picture we call as cross Nicol picture or cross polarized light with both filter. You can see that microcrystallite in my aggregate. You also can see micro crack, a little bit of micro crack here, and a little bit of micro crack here. And this is we call as plain light with first picture. You can see the formation of a bubble everywhere, but my semi-paste and is hard, dense, and tightly bound to the aggregate. So I can conclude that the examiner sample show the evidence of cracking and formation of microcrystallite in aggregate and semi-paste. Alkali silica gel has not been positively identified, but the formation of microcrystallite of silica been detected in aggregate. Okay, go to the next one. For the ordinary concrete grade 25, this one is really, I think I can call it as one of masterpiece because I discover alkali silica reaction. I just discovered alkali silica reaction in my aggregate. And alkali silica reaction is happen when aggregate react with alkali hydroxide in concrete and full gel get swelling and absorb water from the surrounding. So we can see the alkali silica aggregate in the cross nickel picture. You can see it's totally full with water because it's absorbed water and it's swelling. So it's a circle of water here. And here you can see the formation of a bubble everywhere. And for my ordinary, okay, for this one, you can see there also micro crack, microcrystallite in my aggregate, but the cement paste is hard, dense, and tight bondly to the aggregate. So for the next one, okay, this for ordinary concrete grade 35. My ordinary concrete grade 35, I can see a lining crack, a long lining crack, and here, and also a few outer aggregate. I think this coarse aggregate, they crack and start to become smaller pieces during the vibration. So that's why you can't see much coarse aggregate compared to the grade 35 and grade 44, grade 25 and 44. So I doing some research, and some of petrographers say that with the addition of fine aggregate, the concrete becomes stronger. So I think maybe that's why my concrete aggregate 35 is stronger than 44. It's a lot of aggregate, and it's also the semi-paste is hard, dense, and tightly bonded to aggregate. But the air bubbles in this concrete is a little bit higher compared to other concrete. And one another thing, based on this picture, I made a calculation for water, estimation of water to concrete cement, and it's estimate around 2.5 to 0.25 to 0.3. But meanwhile, while doing the calculation, is water cement content supposed to be 0.49. So I think my concrete is it made me scared. So the examination showed the evidence of cracking aggregate in the cement paste. Alkali silica gel has not been positively identified, but the aggregate is already altered. Okay, so the last one is for grade 44. As you can see here, it's full with aggregate. It's so nice, but there's a long liney crack here, and I found this interesting thing, which is aggregate. That's how they mention. Aggregate is hydrous calcium aluminium or cement bacillus, we call it, caused by the sulfate attack on concrete. And the presence of aggregate is actually, there's a lot of present in another picture, but I take this one because I want to show the crack lining. And this aggregate actually led to a tensile stress reducence and expansion of the whole system, crack, and lead to the total collapse of the concrete. That's why I think this concrete is supposed to be higher than grade 35, but it's become lower density and compression because of the presence of aggregate. But the other part is just nice. The cement is dense and tightly bonded to aggregate. A bubble thread in the aggregate is so the examination samples show the evidence of cracking on the aggregate. It's obviously cracking. You can see that. Kali silica gel has been not positively identified, but the presence of a bubble and microcrystallite and aggregate detected in aggregate. In aggregate. So for the future work, I already start my future work. First of all, I'm gonna irradiate the sample at Nuclear Malaysia, so I can see the difference between before and after the irradiation, how the morphology and the structure. I also send my concrete for another test like XRF, SRD, and FISEN. And I'm suggested whoever use my concrete because I gonna give some concrete to my junior to doing simulation and HBL test to know what the optimum thickness that we can use for the shielding. Okay, this is some reference, and I forgot to put conclusion. I think, and that's all.
Thank you, Miss Naswa. When I see all the pictures you fabricate the concrete, it gives me some good memories because I do same ferroboron concrete. I think you do that in agency
Just now
detail.
before you present, I just want to ask about your recipe of boron concrete, but because I nervous, I can type. I will type the question. So
Yeah, I think I fabricate my ferroboron the same instrument as you in agency Dengkil.
Same.
So I just want to ask maybe one question because we already exceed our time. So how many sample that did you test for the compression test?
For compression test, I'm using 3 sample for each type of concrete.
Oh,
Three.
so the
Supposed to have
average
minus 4.
value for that grade 35 is 44 something like that. Okay.
Actually, I'm doing this before MCO. It take me 1 year before MCOs. When I'm doing grade 35, the MCO already start. So I have to stop my project, and the curing process become more than 100 days compared to 28 days. So
Yeah,
it's so
maybe
affect my concrete. And after the MCO, we changed the cement type, Portland cement type, because all the material has been expired.
yeah. So because I think for the compression test, we have to do that test exactly 28 days after the curing. But nevertheless, yeah, MCO happened. We cannot handle that. Maybe you can suggest for your junior to redo the sample. But maybe if we may have 2 minutes for next question. So this is from Dr. Amira. So how you optimize the volume per percentage of gravel, cement, aggregate water in concrete? Because it shows in the petrographic image not consistent. Furthermore, it will show an effect if it is used for radiation purposes.
Can I answer the question in the chat? I will type.
Yeah. Maybe you can stop sharing. The question is in the chat.
Okay, thank you.
Okay, Ms. Naswa, if you can answer that question, or maybe if you can contact personally with Dr. Amira. Actually, Dr. Amira is from TSM. Okay, in the meantime, I would like to thank all the participants because staying with us up until the end of the presentation. I'm sorry on behalf of the organizing committee because we are exceed to the time. Okay, we should stop at 1 o'clock. But yeah, you all stay. So I would like to thank you. Okay. So Ms. Naswa, if you want to address Dr. Amira's question, or you want to pass it. So how you to open the volume? Yeah, like Dr. Amir said, I also see the inconsistent in the sample. Okay. But before this, I didn't do that petrography image. Okay. But maybe in the future, I can consider that test. So Ms. Naswa, or maybe she having the same problem with her mic. Okay. So I think if not, we have to stop now because we already exceed 50 minutes. So because we have another session for the afternoon, we will start around, if I can check. So the afternoon will start at 2:10 p.m. So I hope that everyone can still join for the afternoon session. So the session will be on the material and sustainability that will be chaired by Dr. Julie from Malaysian Nuclear Agency. So yeah, once again, I would like to thank everyone and I hope that everyone can continue join the iNUSTEC 2021 right after lunch break. So thank you and have a good rest.